Did you know that for every grain of sand on Earth, there are approximately 10,000 stars scattered across our Milky Way? Or that deep within its core, an enormous black hole hides, an invisible but incredibly powerful force shaping our galaxy? Join us as we venture through the vastness and wonder of the Milky Way, uncovering its mysteries and hidden secrets. The Milky Way is often described as a barred spiral galaxy, distinguished by its winding arms that stretch outward from a central bulge. This bulge, a dense cluster of stars, plays a vital role in the galaxy's shape. The Milky Way spans about 100,000 light-years in diameter, a colossal stretch of space teeming with billions of stars, gas, and dust. Though it's hard to view the entire galaxy from Earth, astronomers have mapped its structure through sophisticated techniques, including observations from space telescopes. This research has revealed that the Milky Way isn't a perfect disk. It has a subtle warp and unevenness, shaped by gravitational interactions with neighboring galaxies and the mysterious dark matter that permeates the galaxy. Dark matter, though invisible and undetectable by traditional means, exerts a profound gravitational influence on the Milky Way, playing a crucial role in its structure. The Milky Way's total mass, including stars, gas, dust, and dark matter, is estimated to be around 1 trillion times the mass of our Sun, holding the galaxy together and influencing the orbits of stars and other celestial objects within it. But the Milky Way is not alone. It is part of a collection of galaxies known as the Local Group, which contains more than 50 galaxies, with the Andromeda Galaxy being the largest. This group is just one of many clusters of galaxies scattered across the universe, reminding us of the incredible scale and complexity of the cosmos. Within the Milky Way, estimates suggest there are between 100 billion and 400 billion stars. Despite the sheer number, our understanding of these stars remains limited. Many are too faint or distant to observe directly, so astronomers rely on methods like star surveys, which detect stars by their brightness and distance. However, interstellar dust often clouds our view, obscuring large regions of the galaxy and making it difficult to account for every single star. The galaxy is home to a diverse range of stars, some massive and blue, others smaller and red. Interestingly, red dwarfs, the most common type, are faint and long-lived, making them especially hard to detect. In fact, many scientists believe that most stars in the Milky Way are red dwarfs, but their dimness complicates our understanding of the galaxy's stellar population. Alongside these stars, the Milky Way is filled with stellar remnants, white dwarfs, neutron stars, and black holes that represent the final stages in the life cycle of stars. Each of these remnants adds complexity to the galaxy's makeup, contributing to the intricate tapestry of its evolution. At the very heart of the Milky Way lies a supermassive black hole known as Sagittarius A. With a mass approximately 4 million times that of our Sun, it dominates the center of our galaxy. The discovery of Sagittarius A revolutionized our understanding of the Milky Way. In the 1980s, astronomers began observing unusual movements of stars near the galactic center, which suggested the presence of a massive unseen object. Further studies and advanced mathematical models confirmed that a supermassive black hole was indeed lurking at the core. In the following decades, telescopes like the Very Large Array and infrared observatories provided even more detailed observations, revealing star clusters orbiting the black hole. In 2018, the Event Horizon Telescope captured the first ever image of a black hole's shadow, marking a monumental achievement in astrophysics. While the image was of a black hole in a distant galaxy, it helped deepen our understanding of these enigmatic objects, including Sagittarius A* and its role in shaping the Milky Way. The study of Sagittarius A* offers scientists a unique opportunity to explore the nature of gravitational forces, galaxy formation, and the evolution of cosmic structures. By continuing to observe and analyze this black hole, we gain critical insights into the processes that govern the universe at its largest scales. The Milky Way is in constant motion, rotating at an impressive speed of about 270 kilometers per second, or roughly 600,000 kilometers per hour, at the location of our solar system. This rotation is driven by the galaxy's massive gravitational pull, which includes the combined weight of stars, gas, dust, and dark matter. However, the speed at which different regions of the galaxy rotate varies. The stars closer to the center rotate faster, while those farther out, like our Sun, move more slowly. The solar system's orbit around the galactic center takes roughly 250 million years to complete, a journey known as a galactic year. This rotation is not just a curious fact, it plays a critical role in maintaining the galaxy's structure. As the Milky Way spins, the centrifugal force of this motion helps counteract the gravitational pull of the galaxy's mass, stabilizing the spiral arms and allowing the galaxy to maintain its stunning shape. The Milky Way is not just a galaxy, it's a living, dynamic entity, full of stories waiting to be told. From its glowing stars to the hidden dark matter, from the mysterious black hole at its core to the stars that light its arms, our galaxy is a true marvel of the cosmos, offering endless opportunities for discovery. The movements of stars and gas clouds within the Milky Way's spiral arms offer astronomers a crucial tool in mapping the galaxy's mass distribution. This includes uncovering the mysterious dark matter halo that wraps around the galaxy. By studying how the galaxy rotates, scientists can peer into the Milky Way's past, present, and future. The rotation reveals how galaxies evolve and interact through gravitational forces, allowing us to better understand the birth and life cycles of stars and galaxies across cosmic time. Furthermore, examining galactic rotation contributes to our broader understanding of the universe itself. It uncovers the gravitational forces that sculpt galaxies, from their formation to their eventual death. This study reveals how the universe's vast structures develop, survive, and interact with one another. The Milky Way can be broken down into several distinct regions, each contributing uniquely to its overall structure and behavior. These regions, the galactic bulge, the disk, the halo, and the spiral arms, each serve an important purpose in shaping the galaxy's life cycle. At the center lies the galactic bulge, a dense region of stars, primarily older red giants. This spherical structure houses Sagittarius A, the supermassive black hole at the heart of the Milky Way, which has a profound effect on the orbits of nearby stars. The bulge's formation is believed to date back to the galaxy's early years, making it a vital area for studying stellar evolution and dynamics. Surrounding the bulge is the disk, a flat and rotating region where most of the galaxy's younger stars, gas, and dust reside. This area is the heart of star formation, constantly fueling the galaxy's energetic and colorful appearance. The spiral arms of the disk are particularly dynamic, rich with young, hot stars and active star-forming regions. These arms contrast starkly with the older, more stable stars found in the bulge, creating a visual tapestry that reflects the galaxy's ongoing growth and transformation. Beyond the disk is the galactic halo, a vast spherical region that surrounds the entire galaxy. The halo contains some of the oldest stars, globular clusters, and a significant amount of dark matter, thought to constitute much of the galaxy's mass. Unlike the dense disk, the halo is sparsely populated, with stars that are predominantly metal-poor, a sign of their formation in the early universe. This region plays a key role in shaping the Milky Way's gravitational structure and its evolutionary path. Each of these regions provides crucial insights into the forces that drive galactic evolution. The diversity within these areas highlights the Milky Way's complexity, demonstrating how different environments influence the formation and development of stars and structures across the universe. Through these varying regions, we see how conditions can shape the evolution of galaxies on both a small and cosmic scale. The Milky Way, estimated to be around 13 billion years old, ranks among the older galaxies in the universe. Scientists have pinpointed its age using several techniques, most notably by studying the oldest stars found in globular clusters and the galactic bulge. Globular clusters are spherical collections of stars that orbit the galaxy. Many of these clusters are ancient, some dating back to nearly the birth of the universe itself, around 13 billion years ago. By studying the oldest stars within these clusters, astronomers can estimate when they first formed. This, in turn, provides a lower limit for the Milky Way's age. Another key method involves analyzing the chemical composition of stars. As stars evolve, they produce heavier elements through nuclear fusion. The oldest stars, which formed during the galaxy's infancy, contain fewer of these heavy elements, indicating they were born in a primordial environment. By examining these stars and their elemental makeup, astronomers can infer the timeline of the Milky Way's formation. This approach reveals a remarkable finding. The Milky Way began its formation only a few 100 million years after the Big Bang, a testament to how quickly the universe began to form complex structures. This deeper understanding of the galaxy's origins not only offers insight into the Milky Way's past, but also provides a roadmap for studying other galaxies, revealing the processes that shape the universe itself. The study of the Milky Way's structure and the distribution of its components offers us crucial clues about its past. Observations of gradients in age and composition across different regions of the galaxy help us uncover how and when these areas formed. By continuously monitoring stellar movements and interactions, scientists refine age estimates, painting a detailed picture of the Milky Way's evolutionary history. Understanding the galaxy's age not only places it within the larger timeline of the universe, but also reveals the processes that shaped galaxies and the conditions that existed in the early universe. The future of the Milky Way is a fascinating subject, shaped by both gradual changes and dramatic events. In roughly 4 billion years, the Milky Way is expected to collide with its neighboring galaxy, Andromeda. This gravitational interaction will ignite a series of cosmic fireworks as the two galaxies merge, altering their structures in a spectacular way. While the stars within the galaxies are far enough apart to avoid direct collisions, their gravitational forces will lead to significant changes, sparking the formation of new stars in regions where gas and dust are compressed. As time progresses, this merger will form a larger galaxy, often referred to as Milkdarda, where the remnants of both the Milky Way and Andromeda will settle into a more stable configuration over several billion years. This newly formed galaxy will continue to evolve, with stars reorganizing into new orbits within the merged structure. The distant future of the galaxy, however, is marked by even greater cosmic changes. As the expansion of the universe accelerates due to dark energy, the Milky Way and its newly formed counterpart will drift further apart from other galaxies, eventually becoming isolated in an ever-expanding universe. In tens of billions of years, interactions with nearby galaxies will fade, and the Milky Way in its merged form will be home mostly to older stars. The gas needed for new star formation will be depleted, and the galaxy will experience a slow, gradual decline. The remaining stars will fade, leaving behind a dark and quiet galaxy populated mainly by white dwarfs, neutron stars, and black holes. This long-term decline will represent a far-off yet captivating end to the life of our galaxy. Mapping the Milky Way from within presents its own set of challenges due to our position inside the galaxy's disk. Nonetheless, astronomers have developed various techniques to understand its structure and dynamics. One effective method involves observing light across different wavelengths, including radio, infrared, and optical waves. These wavelengths reveal different components of the galaxy, with radio waves being especially valuable. Radio observations can penetrate the dense dust clouds that obscure parts of the Milky Way, allowing astronomers to map the distribution of neutral hydrogen gas, which is abundant throughout the galaxy. Using the wavelengths emitted by this gas, scientists can produce detailed maps of the galaxy's spiral arms and identify regions of active star formation. Large surveys, such as the HI survey and the Sloan Digital Sky Survey, use radio telescopes and ground-based instruments to generate comprehensive maps of the galaxy's structure. Infrared observations are another crucial tool in mapping the Milky Way. These observations can pass through dust more effectively than visible light, revealing the locations of young stars and areas where new stars are forming. Space telescopes like the Spitzer Space Telescope and the Wide Field Infrared Survey Explorer have played pivotal roles in these efforts, providing clearer pictures of the galaxy's inner workings. In addition to observing light, the study of stellar populations and their movements allows astronomers to create a three-dimensional map of the galaxy. By tracking the positions and velocities of stars, especially those in the galactic bulge and disk, scientists gain valuable insights into the gravitational influences at play. The Gaia satellite, for instance, has contributed significantly to our understanding of the Milky Way, offering precise measurements of the positions, distances, and motions of billions of stars. This has led to the creation of one of the most detailed maps of our galaxy to date. These combined techniques allow astronomers to piece together a more comprehensive view of the Milky Way, revealing a complex and dynamic system. With ongoing advancements in observational technology, new discoveries continue to enrich our understanding of the galaxy's formation, evolution, and the broader cosmic environment in which it exists. The Milky Way is a galaxy unlike any other, with several unique features setting it apart from the rest of the universe. One of its most distinctive characteristics is its spiral structure. As a barred spiral galaxy, the Milky Way features prominent spiral arms that extend outward from a central bar-shaped formation of stars. These spiral arms are teeming with star formation, filled with vast amounts of gas and dust, making them vibrant hubs of cosmic activity. This structure plays a crucial role in star birth and the galaxy's ongoing evolution. At the very heart of the Milky Way lies a supermassive black hole, known as Sagittarius A Sty. With a mass about 4 million times that of the Sun, its gravitational pull governs the movement of stars in the galactic core. This black hole provides astronomers with valuable insights into the behavior of these cosmic objects and their role in shaping galaxy formation. By studying Sagittarius AA and its surrounding environment, scientists continue to deepen their understanding of the complex dynamics at the center of the Milky Way. These discoveries not only offer clues about our galaxy's history, but also broaden our knowledge of black holes and their fundamental role in the universe. The Milky Way, a vast and intricate galaxy, is home to a rich diversity of stellar populations. Within its sprawling arms, a blend of old and young stars can be found. The older stars predominantly reside in the galaxy's central bulge and halo, while the younger stars are concentrated in the disk, especially within the active regions where new stars are constantly being born. This dynamic mix of stellar ages creates a galaxy that is both ancient and ever-evolving. One of the most striking features of the Milky Way is its globular clusters. These tightly packed collections of ancient stars orbit the galaxy, offering us a glimpse into the early days of the Milky Way shortly after its formation. These clusters, remnants of a time long past, reveal clues about the conditions that shaped the galaxy's early evolution. The Milky Way is not a solitary entity in the vast cosmos. It is part of a group of more than 50 galaxies known as the Local Group, which includes the famous Andromeda Galaxy, as well as several smaller galaxies. The interactions between these galaxies are nothing short of fascinating. Gravitational forces between them create tidal effects, which reshape their structures over time. In fact, these interactions set the stage for a future collision with the Andromeda Galaxy, a cosmic event that is expected to take place billions of years from now. This ongoing interaction paints the Milky Way as an active participant in the cosmic dance, evolving alongside its neighboring galaxies. Though the Milky Way has its unique features, it shares many similarities with other galaxies. It belongs to the category of spiral galaxies, specifically a barred spiral galaxy. This is a classification it shares with other well-known galaxies, including Andromeda. The central bar structure of the Milky Way plays a crucial role in the movement of stars and gas within the galaxy, making it a key feature in its dynamic behavior. In terms of size, the Milky Way is considered medium to large by galactic standards. It spans approximately 100,000 light-years across, containing somewhere between 100 billion and 400 billion stars. While some galaxies, like the enormous elliptical galaxy IC 146, are much larger, others are far smaller, like the dwarf galaxies that dot the universe. The Milky Way's position within the Local Group highlights the incredible diversity of galaxies in the universe. One of the most intriguing aspects of the Milky Way is its dark matter halo, which extends far beyond its visible components. This halo, composed of invisible dark matter, is essential for understanding the galaxy's rotation and overall structure. Dark matter, which does not emit light but can be detected through its gravitational effects, is a critical component of many galaxies. Its role in the formation and evolution of galaxies is a key piece of the cosmic puzzle. The Milky Way's history is also marked by interactions with nearby galaxies. Smaller companions, like the Large and Small Magellanic Clouds, have influenced the Milky Way's evolution through gravitational interactions. These encounters, which often result in mergers and exchanges of stars and gas, shape galaxies in profound ways. These interactions can affect everything from star formation rates to the overall structure of the galaxy. Thus, while the Milky Way is unique, it is part of the broader cosmic narrative, shaped by the same forces that guide the evolution of galaxies across the universe. Stars are born in the Milky Way through a complex process that begins in vast regions of gas and dust known as molecular clouds. These clouds, often referred to as stellar nurseries, are the birthplaces of new stars. Within these dense, cold regions, gravity can cause parts of the cloud to collapse under its own weight. As the material condenses, it forms dense cores. The increasing pressure and temperature within these cores eventually reach a critical point, igniting nuclear fusion. Hydrogen atoms fuse into helium, releasing immense amounts of energy. This process marks the birth of a new star, or protostar. As the protostar accumulates mass from its surroundings, it continues to heat up, eventually clearing out the material around it. Once the temperature at the core reaches a high enough point to sustain nuclear fusion, the star ignites and enters the main sequence phase of its life. This is the longest and most stable phase for most stars, where they continue to shine by converting hydrogen into helium through nuclear fusion. Interestingly, molecular clouds are not just sites for the formation of individual stars, but also for the creation of star clusters. In regions of dense gas, multiple stars can form simultaneously, creating groups of stars with similar ages and chemical compositions. These star clusters, which can range in size from dozens to thousands of stars, interact with each other gravitationally, influencing their paths and fates. This dynamic process of star birth and interaction plays a significant role in shaping the Milky Way and provides valuable insights into the life cycles of stars. The Milky Way is home to a wide array of stars, each with its own distinct characteristics. Among the most common are red dwarfs, small and relatively cool stars that make up the majority of the galaxy's population. These stars have incredibly long lifespans, often lasting trillions of years. Due to their small size and low brightness, red dwarfs are difficult to observe without advanced technology. Another significant group of stars in the Milky Way are the main sequence stars, like our own Sun. These stars are in a stable phase of hydrogen fusion and represent a wide range of sizes and temperatures. The main sequence spans a spectrum from the massive and hot O-type stars to the cooler, smaller M-type stars. The lifespans of these stars vary dramatically, with larger stars burning through their fuel much more quickly than their smaller counterparts. Beyond the main sequence, the Milky Way is home to giants and supergiants. Red giants, which are stars that have exhausted the hydrogen in their cores, begin to expand and cool. These stars can be several times larger than the Sun and are much more luminous. Supergiants, like Betelgeuse and Antares, are even larger and more luminous, representing some of the most massive stars in the galaxy. These stars live fast and die young, often ending their lives in dramatic supernova explosions. In addition, the Milky Way is home to a diverse range of stellar remnants that play a pivotal role in shaping its overall structure. White dwarfs, for example, are the remnants of stars that were once small to medium-sized. After exhausting their nuclear fuel, these stars shed their outer layers, leaving behind a dense, glowing core. Neutron stars, on the other hand, are born from the remnants of massive stars that have exploded in violent supernovae. These objects are incredibly dense, consisting almost entirely of neutrons. Finally, black holes, which form from the collapse of the most massive stars, remain some of the most mysterious and fascinating entities in the galaxy. Each of these stellar remnants contributes uniquely to the rich composition of the Milky Way. Their influence extends to the galaxy's dynamics, evolution, and chemical makeup. The fate of massive stars, those with at least 8 times the mass of our Sun, marks a particularly dramatic chapter in the story of the galaxy. Once these stars deplete the hydrogen in their cores, they enter a series of nuclear fusion stages. They fuse lighter elements like helium into carbon, and eventually, heavier elements like oxygen and silicon. This chain of reactions continues until the core becomes composed primarily of iron, a metal that cannot produce energy through fusion. At this critical juncture, the balance between the inward pull of gravity and the outward pressure from fusion reactions tips. Unable to maintain fusion, the core collapses under its own gravity, triggering a supernova, a cataclysmic explosion that outshines entire galaxies for a brief moment. This explosion is not just an impressive burst of light and energy. It releases vast amounts of material, including heavy elements like carbon, oxygen, and iron, into space. These elements, formed in the heart of stars, are crucial for the development of life as we know it. As they spread throughout the interstellar medium, they provide the building blocks for future star and planet formation. The aftermath of a supernova is just as important as the explosion itself. These violent events can trigger the collapse of nearby molecular clouds, sparking the birth of new stars. Shockwaves from the explosion compress surrounding gas, creating the conditions necessary for star formation. In this way, the death of massive stars acts as a catalyst for the ongoing evolutionary processes of the Milky Way. The cycle of creation and destruction continues, shaping the stellar populations and enriching the chemical makeup of the galaxy. Furthermore, the remnants of these massive stars, neutron stars and black holes, have far-reaching effects on their surroundings. Neutron stars, particularly those that spin rapidly, generate beams of radiation from their magnetic poles. These beams, when aligned with Earth, are detected as pulsars, emitting regular pulses of energy that provide astronomers with a window into the behavior of matter under extreme conditions. Neutron stars, the dense cores left behind after a supernova, are among the most fascinating objects in the universe. A neutron star forms when the core of a massive star collapses and nuclear fusion can no longer counteract the force of gravity. What remains is a core so dense that protons and electrons combine to form neutrons. This transforms the core into an object about the size of a city, yet containing a mass greater than that of our sun. A single teaspoon of neutron star material would weigh around 6 billion tons, making these stellar remnants some of the densest known matter in the cosmos. The rapid rotation of neutron stars, sometimes several hundred times per second, causes them to emit beams of radiation. These beams, when aimed at Earth, are detected as pulses. The regular intervals of these pulses allow astronomers to study the physics of extreme environments, offering valuable insights into how matter behaves under the most intense pressures and temperatures. In this way, neutron stars are not only remnants of once mighty stars, but also beacons that provide crucial data about the fundamental laws of nature. As part of the larger galactic ecosystem, neutron stars contribute to the recycling of elements within the Milky Way. They help to enrich the interstellar medium with the heavy elements formed during the earlier stages of their host stars' life cycles. This process plays a critical role in the formation of new stars, planets, and ultimately the conditions that support life. The life and death of stars, especially those that end in dramatic supernovae, are key drivers of the galaxy's ongoing evolution, illustrating the intricate connections between stellar life cycles, chemical enrichment, and the birth of new worlds. Neutron stars, with their immense density and powerful gravitational fields, don't just exist in isolation. Their gravitational influence can extend far beyond their immediate vicinity, impacting nearby stars. This effect can lead to the formation of binary systems, two stars orbiting a common center of mass. In these systems, the interaction between the two objects can result in extraordinary phenomena, such as intense X-ray emissions or the ripples in space-time known as gravitational waves. As we continue to study these enigmatic remnants of collapsed stars, we gain deeper insight into fundamental questions about the nature of matter and the life cycles of stars, ultimately unveiling more about the universe's intricate workings. Binary star systems, two stars bound together by gravity, can arise from a variety of processes. The most widely accepted theory is that they form within the same molecular cloud. As these clouds collapse under their own gravity, they can fragment into smaller regions, each becoming a dense cluster that might give rise to multiple protostars. These nascent stars can, through their gravitational pull, attract each other, eventually forming a binary system. The evolution of binary stars is a complex dance, intricately tied to their orbital dynamics and the characteristics of each star. Initially, if the stars are of similar size and mass, they might evolve in parallel. However, Over time, differences in their masses can lead to significant changes in their paths. One of the most fascinating processes in binary evolution is mass transfer. In this scenario, one star pulls material from its companion, dramatically altering both their life cycles. When there's a significant mass disparity between the stars, one may age much more quickly than the other. The more massive star, having exhausted its nuclear fuel, will likely expand into a red giant, ultimately undergoing a supernova explosion. This catastrophic event can leave behind a neutron star or even a black hole. Meanwhile, the smaller companion star may continue its life cycle, evolving into a red giant long after its partner has perished. Binary systems also play a critical role in the study of stellar populations. By observing these pairs, astronomers can determine the masses and ages of the stars based on their gravitational interactions. This knowledge is vital for understanding stellar evolution and the broader characteristics of the galaxies in which these stars reside. The interactions between the two stars can also lead to exotic phenomena, such as the creation of cataclysmic variable stars, or the emission of gravitational waves when compact objects like black holes or neutron stars collide. On the other hand, brown dwarfs occupy a fascinating niche between the largest gas giants and the smallest stars. These objects form in much the same way as stars, by the collapse of gas clouds. However, they lack the mass needed to ignite hydrogen fusion at their cores, which is the defining feature of true stars. Typically, their mass ranges from about 13 to 80 times that of Jupiter. While brown dwarfs may initiate fusion of deuterium, a heavier isotope of hydrogen, this process is short-lived. Despite not being classified as stars, brown dwarfs hold immense scientific value. They serve as a bridge between stars and planets, offering critical insights into both stellar and planetary formation. Studying brown dwarfs helps scientists understand the processes that govern the birth of stars, the dynamics within star-forming regions, and the limits of stellar formation itself. Moreover, brown dwarfs play a significant role in the search for exoplanets. A surprising number of brown dwarfs are found near stars, offering astronomers a unique opportunity to investigate how these different types of celestial bodies interact. The characteristics of brown dwarfs can also shed light on the environment in which planets form, as many exoplanets have been discovered in systems that include brown dwarfs. This has enriched our understanding of the diverse planetary systems that populate our galaxy. Brown dwarfs present some of the most intriguing atmospheric phenomena in the cosmos. These substellar objects, which don't quite qualify as stars, exhibit weather patterns and intricate chemical compositions. Some of their characteristics closely resemble those of the gas giants Jupiter and Saturn. By studying brown dwarfs, researchers are unlocking insights into the atmospheric processes that govern not only these objects, but also planetary atmospheres across the universe. This exploration expands our understanding of both our solar system and the far-flung systems beyond. Furthermore, it provides vital clues about the potential for life elsewhere in the cosmos, offering us a clearer picture of where and how life might arise. Stars, the cosmic foundries of the universe, are responsible for the creation of nearly all the elements we observe. Within the cores of stars, nuclear fusion unfolds under extreme conditions of heat and pressure. This unique environment facilitates the collision and fusion of atomic nuclei, beginning with hydrogen, the most abundant element in the universe. As hydrogen nuclei merge, they form helium, releasing a tremendous amount of energy in the form of light and heat, causing the star to shine brightly. As stars evolve, the conditions in their cores become even more extreme, allowing them to fuse heavier elements. Once hydrogen is depleted, helium fusion takes over, producing carbon and oxygen. With higher temperatures, stars can continue this cycle, creating increasingly heavier elements like neon, magnesium, and iron. Each new fusion phase releases energy, counteracting gravitational collapse and sustaining the star. The story of a massive star's life takes a dramatic turn when it reaches the end of its nuclear fuel. For stars with more than 8 times the mass of our Sun, their final act is a supernova, a catastrophic explosion that generates extraordinary temperatures and pressures. In this explosive death, elements heavier than iron, like gold, silver, and uranium, are forged in rapid neutron capture processes. The shock waves from this event scatter these newly formed elements throughout space, enriching the interstellar medium with materials that will go on to form future stars and planets. Smaller stars like our Sun end their lives in a less violent but equally transformative way. As they become red giants, they contribute lighter elements like carbon and oxygen to the cosmos. The material they expel will eventually become part of the next generation of stars and planets, continuing the cosmic cycle of stellar birth and death. This cycle ensures that the universe is constantly replenished with a rich array of elements, the building blocks for life and all the complexities of the cosmos. The life of a sun-like star begins in a molecular cloud, a dense region of gas and dust in space. Under the force of gravity, parts of this cloud collapse, forming clumps that evolve into protostars. During this phase, the core of the protostar gains mass and heats up, while material from the surrounding region continues to fall inward. When the core reaches the right temperature and pressure, nuclear fusion begins, turning hydrogen into helium. This marks the star's entrance into the main sequence phase, where it will remain for around 10 billion years for a star of solar mass. As the hydrogen in the core gets used up, the core contracts and heats up while the outer layers begin to expand. This signals the star's transition into the red giant phase. At this stage, helium builds up in the core, and when the temperature rises enough, helium fusion begins, creating carbon and oxygen. The outer layers continue to expand, and the star may lose significant mass through powerful solar winds. This reshapes the star's outer envelope. Eventually, a sun-like star exhausts its helium supply and can no longer sustain fusion beyond carbon and oxygen. It begins its slow decline, expelling its outer layers into space to form a planetary nebula, a stunning shell of gas and dust. This nebula contributes to the recycling of material in the galaxy, enriching future generations of stars. What remains is the star's dense core, a white dwarf composed mostly of carbon and oxygen. Over billions of years, the white dwarf will gradually cool and fade, becoming a cold, dark stellar remnant. The entire life cycle of a sun-like star is a testament to the remarkable transformations it undergoes and its crucial role in enriching the universe with elements that will foster the formation of new stars and planetary systems. This cycle, known as the cosmic cycle of matter, illustrates the ever-changing nature of stellar matter and its contribution to the evolving universe. Globular clusters, which are densely packed groups of stars, orbit galaxies and are typically among the oldest stellar populations in the universe. They are believed to form early in a galaxy's history, likely during the intense star-star formation periods that characterize the early universe. The prevailing theory suggests that globular clusters arise from massive gas clouds that collapse under gravity, triggering a rapid burst of star formation. This process results in a dense, tightly bound cluster of stars. As globular clusters evolve, their stellar populations undergo various processes that impact their characteristics and dynamics. Initially, the majority of stars within a globular cluster share similar ages and compositions because they originated from the same molecular cloud. However, as time progresses, stars undergo significant transformations. Massive stars, for instance, burn through their nuclear fuel more quickly, eventually becoming red giants. As they exhaust their fuel, their cores collapse and their outer layers expand before they meet dramatic ends as supernovae, neutron stars, or black holes. These explosive events not only mark the final chapter in the life of a star, but they also reshape the mass distribution within star clusters. Over time, such events can result in the creation of stellar remnants at the heart of these clusters. Another crucial aspect of globular cluster evolution lies in the dynamic interactions between stars. Because the stars in these clusters are densely packed, gravitational forces lead to encounters where stars exchange energy and momentum. This constant exchange triggers an ongoing process. Some stars are flung out of the cluster, while others spiral inward, eventually sinking toward the center. This creates an increasingly dense core region, and over billions of years, it helps sculpt the overall structure of the cluster. This gradual process is known as cluster evaporation. These clusters don't evolve in isolation. Their interactions with the host galaxy further shape their destiny. As globular clusters orbit within their galaxy, they experience tidal forces that stretch or distort their shapes. These clusters are generally found in the spherical halos surrounding galaxies, and their encounters with the galaxy's gas and dark matter lead to additional dynamical changes. Collectively, the effects of stellar evolution, gravitational interactions, and galactic influences converge to produce the distinctive characteristics of globular clusters. For astronomers, these clusters are invaluable tools, offering key insights into the formation and evolution of galaxies. One fascinating outcome of studying globular clusters is the discovery of some of the oldest stars in the Milky Way. These ancient stars, known as population 2 stars, can be found in globular clusters, with some dating back more than 12 billion years to the early phases of the universe, shortly after the Big Bang. Among these ancient stars, BD plus 17 degrees 32248 stands out. It is often cited as the oldest known star, with an age exceeding 13 billion years. This star gives astronomers a direct window into the conditions of the early universe, helping them understand the chemical composition of the Milky Way during its infancy. These stars, with their low metallicity, are thought to contain very few heavier elements, a reflection of the fact that the universe at the time was primarily composed of hydrogen and helium. Studying these ancient stars helps scientists understand the processes behind the creation of elements in the early universe. It also sheds light on how the first stars and supernovae enriched the surrounding interstellar material with heavier elements. In addition to their role in understanding the universe's past, these stars serve as cosmic chronometers. By comparing their ages with those of globular clusters, astronomers can build a timeline of star formation and the evolution of the Milky Way. This provides a deeper understanding of the cosmic environment during the early universe, including the birth and death of stars and the formation of galaxies. The importance of these ancient stars goes beyond understanding the past. They also offer vital clues about the formation of stellar systems and the potential for life elsewhere in the universe. The long-lived nature of these stars means they have withstood the passage of time, offering a unique window into the processes that govern stellar evolution. Their study not only deepens our understanding of the cosmos, but also highlights the path that led to the intricate structures we see today. In our own galaxy, planetary systems are common. Recent discoveries suggest that most stars have at least one planet, and some studies propose that more than half of the stars in the Milky Way host planets. With hundreds of billions of stars in our galaxy, this translates to potentially hundreds of billions of planets. These planetary systems display a wide variety of configurations, from single planets orbiting close to their stars to more complex systems with multiple planets. The advent of space telescopes, particularly the Kepler Space Telescope, has revolutionized our understanding of planetary systems. Kepler's data led to the discovery of thousands of exoplanets, revealing the astonishing diversity of planets in terms of size, composition, and orbital characteristics. Many stars are now known to host multiple planets, which suggests that planetary systems like our own are likely far more common than previously thought. Interestingly, the distribution of planets is not uniform across the galaxy. Different types of stars show different probabilities of hosting planets. For example, red dwarfs, the most abundant type of star in the Milky Way, have been found to have a higher prevalence of planets compared to more massive stars. Factors like the star's mass, age, and environment all influence the likelihood of planet formation, helping astronomers refine their understanding of where and how planets emerge throughout the cosmos. Moreover, current research is delving ever deeper into the fascinating characteristics of exoplanets. Scientists are particularly intrigued by the so-called habitable zone, the region around a star where conditions might be just right to support liquid water, the essential ingredient for life as we know it. As more and more planetary systems are studied, astronomers remain hopeful that they will uncover an abundance of new worlds, some of which could bear striking similarities to Earth. This ongoing investigation into planetary systems is expanding our understanding of the cosmos and raising compelling questions about the potential for diverse forms of life beyond our own planet. The discovery of exoplanets has unveiled an astonishing variety of planetary types, each revealing the vast diversity of worlds that populate our galaxy. Among the most commonly identified categories are gas giants, planets similar to Jupiter and Saturn in our own solar system. These massive worlds are predominantly made of hydrogen and helium and are often encircled by elaborate systems of rings and moons. Some gas giants have been discovered in close orbits around their stars, earning the classification of hot Jupiters. These planets endure extreme temperatures due to their proximity to their stars, creating conditions vastly different from anything observed in our solar system. In addition to gas giants, a significant number of smaller rocky planets, known as terrestrial exoplanets, have been found. These worlds possess solid surfaces, much like Earth and Mars. Many of the terrestrial exoplanets discovered so far lie within the habitable zones of their stars, where conditions could allow for liquid water to exist. Some of these planets are even categorized as Earth-like, sparking increased interest in their potential to host life. But beyond these categories, scientists have also identified a class of planets known as super-Earths. These planets, larger than Earth but smaller than gas giants, typically range in size from 1 to 10 times Earth's mass. Super-Earths may have diverse characteristics such as solid surfaces, thick atmospheres, or even oceans. The discovery of these worlds has expanded our understanding of planetary formation and the conditions necessary to support life. Another intriguing category includes mini-Neptunes, which are smaller versions of Neptune. These planets often have thick atmospheres composed of hydrogen and helium and lie between super-Earths and gas giants in terms of mass and size. Their study raises questions about their formation processes and atmospheric dynamics. The ongoing exploration of exoplanets continues to yield new findings, each one enhancing our understanding of planetary systems, not just within the Milky Way, but also the potential for alternative forms of life scattered throughout the universe. Scientists use a variety of methods to detect and study these distant worlds, employing principles of astronomy and physics. One of the most effective techniques is the transit method. In this approach, astronomers monitor the brightness of a star over time. When a planet passes in front of its host star, it causes a temporary dip in the star's brightness, known as a transit. By measuring the amount of light blocked and the duration of the transit, scientists can infer details about the size of the planet and its distance from the star. Another widely used method is the radial velocity technique. This method detects the gravitational influence that a planet exerts on its host star. As a planet orbits, its gravitational pull causes the star to wobble slightly, a motion that can be detected by shifts in the star's light spectrum, known as the Doppler effect. By analyzing these shifts, astronomers can determine the planet's mass and its orbital characteristics, offering insights into the planet's composition and its potential habitability. Direct imaging is another crucial technique, though it is more challenging. In this method, astronomers use advanced instruments to capture images of exoplanets directly, often by blocking out the light from the star and allowing the dimmer light from the planet to shine through. While this approach has been successful in detecting giant exoplanets, it remains difficult due to the overwhelming brightness of stars. Once an exoplanet is detected, scientists employ spectroscopic analysis to learn more about its atmosphere. By studying the light that passes through an exoplanet's atmosphere during a transit, researchers can identify elements and compounds such as water vapor, carbon dioxide, and even potential biosignatures. This analysis provides critical information about the conditions on these distant worlds and their potential to support life. These various methods combine to offer a comprehensive understanding of exoplanets, helping us appreciate the incredible diversity of planetary systems within our galaxy. The concept of the habitable zone, often referred to as the Goldilocks zone, is crucial in the search for extraterrestrial life. This is the region around a star where conditions are just right, neither too hot nor too cold, for liquid water to exist on a planet's surface. Liquid water is considered one of the key ingredients for life, as we know it. The boundaries of the habitable zone depend on the star's luminosity, temperature, and size, all of which influence the amount of heat and light reaching orbiting planets. For stars similar to our Sun, the habitable zone typically lies at a distance of about 1 astronomical unit, the average distance from Earth to the Sun. However, the habitable zone around a star can vary drastically, depending on the type of star. For instance, red dwarfs, which are cooler and less luminous than our sun, have much closer habitable zones, often within a range of just a few tenths of an astronomical unit. In contrast, for more massive and hotter stars, the habitable zone lies farther out. These stars emit far more energy and heat, which pushes the habitable zone outward. The width of this habitable zone can also fluctuate based on the temperature of the star. In the case of cooler stars, the habitable zone may extend much farther out, as planets in these regions can still maintain surface temperatures that support liquid water, despite the star itself emitting less energy. However, for hotter stars, the habitable zone becomes narrower, and planets must be situated just right to avoid extreme conditions that would make it too hot for water to remain liquid. Environmental factors play a crucial role in determining whether a planet within the habitable zone can truly sustain life. Elements such as the planet's atmosphere, surface pressure, and geological activity significantly affect its climate, and in turn, the presence of liquid water. As astronomers continue to find exoplanets within various habitable zones around different stars, the concept of habitability is evolving. We're beginning to understand the complex interplay of planetary environments and the potential for life in many forms across the vast expanse of the universe. Yes, several Earth-like planets have been discovered within the Milky Way, particularly those nestled in the habitable zones of their respective stars. These planets, often referred to as potentially habitable or Earth analogs, share key characteristics with our planet: size, composition, and distance from their stars. This similarity raises compelling questions about their potential to support liquid water and, by extension, life. One of the most notable examples is Kepler 186f, discovered by the Kepler Space Telescope. Kepler 186f orbits a red dwarf star located approximately 500 light-years away from Earth. With a size about 1.1 times that of Earth, this planet resides within its star's habitable zone, making it a prime candidate for further study in terms of habitability. Another exciting discovery is Proxima Centauri b, which orbits Proxima Centauri, the closest known star to the Sun. Although Proxima Centauri b is similar in size to Earth and lies within its star's habitable zone, its proximity to a red dwarf star presents potential challenges. Stellar flares and radiation from Proxima Centauri could significantly affect the planet's atmosphere, possibly hindering its ability to support life. TRAPPIST-1 is an extraordinary planetary system, hosting 7 planets that are similar in size to Earth. Among them, 3 lie within the habitable zone of its ultra-cool red dwarf star. This position opens up remarkable opportunities to explore how planets evolve and what factors make them potentially habitable. As we continue the search for Earth-like worlds, the upcoming advancements in telescopic technology and observational techniques give astronomers hope to identify even more candidates. Studying these planets not only helps us assess their potential for supporting life, but it also deepens our understanding of planetary formation and the complex dynamics that shape planetary systems across the galaxy. Each new discovery brings us closer to unraveling the intricate puzzle of what makes a planet truly habitable and provides a broader perspective on our own place in the vast cosmic landscape. Gas giant planets form through a fascinating process, starting with the creation of a protoplanetary disk around a young star. This disk, composed of gas and dust, acts as a nursery where solid materials come together to form the cores of planets. In the case of gas giants, this formation process is triggered when a solid core reaches a critical mass, often estimated to be around 10 times the mass of Earth. Once this threshold is crossed, the core begins to attract gas from the surrounding disk through its strong gravitational pull. This leads to the rapid accumulation of hydrogen and helium, forming a massive gaseous envelope that envelops the planet. The location where gas giants form is crucial in determining their evolution. Many gas giants form beyond the frost line, a boundary beyond which temperatures are low enough for volatile compounds like water and methane to condense. This allows the planet to gather additional mass. Beyond this line, the gas giant can more easily attract and retain materials, allowing for the development of a substantial atmosphere. The specific conditions of the protoplanetary disk, such as its density and temperature gradients, play a key role in determining where gas giants will form. Migration is another significant process in the development of gas giants. Once formed, these planets can undergo planetary migration, a phenomenon where their orbits change due to gravitational interactions with the disk or other planets. One common type of migration is called Type 1 migration, where a gas giant interacts with the gas in the protoplanetary disk, causing it to move either inward or outward, depending on the torque exerted by the material. This could lead to gas giants shifting to orbits closer to the star, or perhaps altering their orbital configuration entirely. A more dramatic form of migration is Type 2 migration, which occurs when the planet's mass is large enough to clear a gap in the protoplanetary disk. In this case, the gas giant moves steadily through the disk material, shifting its orbit and potentially changing the structure of the entire planetary system. Depending on the surrounding environment, gas giants may end up in various orbital configurations, from hot Jupiters, gas giants located very close to their stars, to more traditional planetary layouts like those seen in our own solar system. These migrations are not only key in determining planetary system architecture, but are also critical in understanding the wide diversity of planetary systems observed throughout the Milky Way. Hot Jupiters are a striking example of gas giants that defy expectations. Similar in size and composition to Jupiter, they orbit much closer to their parent stars, leading to significantly higher temperatures. Typically, these gas giants have orbital periods of just a few days or weeks, often located within 1/10 of an astronomical unit from their stars, where extreme heat levels prevail. Surface temperatures can reach over 1,000 degrees Celsius, creating environments vastly different from those of gas giants in our solar system. The existence of hot Jupiters has puzzled astronomers. Initially, most planetary formation models suggested that gas giants would form in cooler regions beyond the frost line, where conditions would allow for the accumulation of volatile materials like water and methane. To find such massive planets so close to their stars was unexpected and raised questions about how they could have formed. The prevailing theory is that these planets might have formed farther out, beyond the frost line, before migrating inward. However, the mechanisms driving such dramatic shifts in their orbits remain a subject of active research, as astronomers continue to explore the origins and evolution of these extraordinary worlds. Moreover, the discovery of hot Jupiters has dramatically challenged previous assumptions about the dynamics within planetary systems. These extreme planets, with their blistering temperatures and unusual orbits, force us to reconsider what we know about how planetary systems evolve. The intense radiation and heat that these planets experience can lead to significant atmospheric loss over time. This, in turn, affects their chemical makeup and stability, presenting a unique puzzle for scientists. How do these atmospheres evolve in such extreme conditions? And what happens to their weather patterns when subjected to such intense stellar environments? These questions have sparked a new wave of inquiry into the fate of gas giant atmospheres. The presence of hot Jupiters has completely transformed our understanding of planetary formation and migration, prompting the development of entirely new theories. These discoveries underscore just how diverse planetary systems can be, far more complex than anyone previously imagined. As astronomers push forward in their study of hot Jupiters, they are uncovering critical insights not only about the formation of these distant worlds, but also about the forces that shape all exoplanets. This growing body of research is slowly piecing together the intricate puzzle of planetary evolution. As we continue to learn more about these enigmatic giants, scientists are gaining valuable knowledge of the broader processes at play in planetary formation. Each new discovery adds another layer of understanding, revealing the variety of ways in which worlds can evolve, often in ways that challenge our most basic assumptions. Planetary rings are another intriguing aspect of these distant worlds. They are captivating structures that can form around some planets through a variety of processes. One primary mechanism is the accumulation of material in a planet's vicinity, which can occur when a moon or comet strays too close to a planet and is torn apart by tidal forces. This phenomenon, known as tidal disruption, happens when the gravitational pull of the planet overcomes the forces that hold the moon or comet together. The resulting debris creates a stunning ring system around the planet. Rings can also form through collisional events when moons collide with other celestial objects like asteroids or comets. The debris from these collisions can spread out, eventually forming a ring around the planet. And as these particles collide with one another, they can break into even smaller pieces, further enriching the material within the ring system. Over time, the ring can grow more complex, with particles ranging from tiny dust grains to larger chunks of ice and rock. The gravitational influence of moons plays a critical role in maintaining the structure of these rings. Some moons, known as shepherd moons, exert gravitational forces that help confine ring material to specific regions. These moons prevent the particles from spreading out or being pulled into the planet, effectively shaping the ring's structure. As a result, gaps and wave patterns often form within the rings, giving them a visually striking appearance. Environmental factors such as the planet's magnetic field, solar radiation, and the presence of other celestial bodies also influence the evolution and longevity of planetary rings. Over time, interactions between ring particles and these external forces can reshape the structure and dynamics of the ring system. As astronomical research continues, the study of planetary rings offers critical insights into the processes that shape not only individual planetary systems, but the broader universe. Finally, rogue planets, those wandering free through space without a parent star, add another layer of mystery to our understanding of planetary bodies. These rogue worlds have drifted away from their original star systems and now roam the galaxy on their own, unattached to any star's gravitational pull. Rogue planets can form in a variety of ways, but are often believed to have originated in protoplanetary disks. Gravitational interactions, such as collisions with other planets or close encounters with stars, can eject these planets from their parent systems, sending them into the vast emptiness of interstellar space. Their existence challenges our understanding of planet formation, suggesting that the universe might be filled with hidden worlds, wandering through the cosmos without a star to call home. And some rogue planets may have formed independently, isolated from any star, accumulating mass from the surrounding gas and dust during their early formation stages. Estimates suggest that these rogue planets could be remarkably common within the Milky Way, possibly outnumbering the stars themselves. Several studies indicate that there may be billions of these unbound worlds scattered throughout the galaxy. The process of planet ejection, where a planet is cast out of its original orbit, might occur far more frequently than once believed. This is especially true in crowded regions of space where gravitational interactions are at their peak. In places like young star clusters or systems with 3 or more interacting bodies, the dynamic environment can cause dramatic orbital shifts. As a result, these celestial bodies may be expelled into the void, roaming the galaxy without the tether of a star. The study of rogue planets offers a fascinating glimpse into the complex processes of planetary formation and the nature of planetary systems. Unlike planets that remain bound to a star, rogue planets can develop unique atmospheres and geological features shaped by their varied and often turbulent histories. Their wandering existence raises intriguing questions about their potential to support life and how they might contribute to the distribution of materials and elements across the galaxy. Recent advancements in observational techniques are beginning to offer new ways to detect these elusive objects. While the challenge remains significant due to their dimness and distance from any nearby star, the hope is that with improved technology and more extensive surveys, astronomers will be able to unveil more about these mysterious worlds and what they can reveal about the broader processes at play in the universe. Planetary moons themselves come into existence through a variety of mechanisms, each contributing to the rich diversity of moon systems observed around different planets. One of the primary ways moons form is through accretion, a process where dust and gas in a primordial disk surrounding a young planet gradually come together to form a solid body. This process mirrors how planets themselves grow in size. As these particles collide and stick together, they can eventually coalesce into moons. Moons can also form through a process called capture. In this scenario, a passing object, often an asteroid or a comet, comes close enough to a planet's gravitational field and is drawn in, becoming a moon. This method is responsible for many of the irregular moons orbiting larger planets, such as those found around Jupiter and Saturn. Additionally, some moons may be the product of debris created by giant impacts. When a large object collides with a planet, the debris ejected during the impact can eventually gather and form a moon over time. The role of moons within their planetary systems is complex and multifaceted. Their gravitational pull can influence a planet's tides, causing fluctuations in its liquid bodies. These tidal forces can have significant impacts on a planet's climate and atmospheric conditions. Moons also offer a window into planetary formation and dynamics. By studying the surface and composition of a moon, scientists can gain valuable insights into the history of its parent planet and the conditions that prevailed in the early solar system. Moons are crucial to understanding the potential for life beyond Earth. For instance, moons like Europa and Enceladus hide subsurface oceans beneath their icy crusts, sparking speculation about the possibility of life elsewhere in the cosmos. By studying these moons, scientists aim to uncover clues that could help answer the age-old question, is there life beyond our planet? Each moon has its own unique story, telling us more about its planet and adding to the intricate narrative of our cosmic neighborhood. The Milky Way's spiral arms are one of the most iconic features of our galaxy, sweeping outward from the galactic center like great, swirling tendrils of stars, gas, and dust. These arms, composed of several main and smaller branches, are home to many young hot stars. As a barred spiral galaxy, the Milky Way has a central bar structure that influences the formation of its spiral arms. The formation of these arms is tied to a phenomenon called density waves. As stars and gas move in their orbits around the galaxy's center, they don't all travel at the same speed. This creates areas where the density of stars and gas is higher, forming the spiral arms we see today. These arms are dynamic, continuously evolving as new stars are born from the gas and dust that accumulate there. Older stars drift into the space between the arms, creating a constantly shifting pattern. This cycle of star formation and stellar movement contributes to the galaxy's vibrant and ever-changing ecosystem. In fact, the spiral arms also impact planetary system formation. As the density waves travel through the galaxy, they cause gas clouds to collapse, leading to new stars. This process increases the chances of planets forming around these new stars, making the spiral arms key players in the galaxy's ongoing evolution. Dark matter, an invisible and mysterious substance, makes up about 27% of the universe's total mass and energy. Unlike ordinary matter, dark matter does not interact with light in any way, meaning it can't be seen through traditional telescopes. Its presence is inferred from its gravitational effects on visible matter, such as the unusual motion of stars and galaxies. In the Milky Way, dark matter plays a critical role in maintaining the structure of the galaxy. Observations show that stars on the outer edges of galaxies move much faster than expected, based on the visible matter alone. This indicates the presence of more mass we cannot detect directly. Dark matter provides the additional gravitational pull needed to keep stars in their orbits and maintain the galaxy's stability. It forms a vast halo around galaxies, stretching far beyond their visible parts, and affects the motion of galaxies and clusters of galaxies. Furthermore, dark matter helps shape the large-scale structure of the universe. Its gravitational influence encourages galaxies to group together in large clusters and form intricate webs of cosmic matter. Understanding dark matter is essential to unlocking the full story of the universe's evolution, as it affects everything from star formation to galaxy dynamics. The galactic halo is an expansive spherical region that surrounds the Milky Way. It contains a mixture of dark matter, ancient stars, globular clusters, and a sparse amount of gas. This halo plays a crucial role in our understanding of the Milky Way's mass distribution and gravitational dynamics. Stars in the galactic halo are typically older and chemically simpler than those in the galaxy's disk, where new stars form from gas and dust. This difference offers valuable insights into the early history of the Milky Way. The presence of globular clusters, dense groups of older stars, provides further evidence that the halo is ancient, possibly formed during the galaxy's early stages of growth. Studying the objects within the halo can reveal much about the Milky Way's formation and its history of accreting mass. By examining their motion and distribution, scientists can piece together a clearer picture of how our galaxy has evolved over billions of years. The motion of halo stars and globular clusters offers a fascinating glimpse into the Milky Way's past. These stars, drifting through the outer regions of our galaxy, carry with them secrets about how the Milky Way interacted with and absorbed material from other galaxies over billions of years. This includes evidence of past mergers and the relationships with smaller galaxies that may have once collided with the Milky Way, contributing both stars and gas to its halo. Recent research into the halo has brought us closer to understanding the enigmatic nature of dark matter. The halo's gravitational influence reveals that dark matter makes up a significant portion of the mass in this region, subtly shaping the dynamics of galaxies. This invisible force extends its reach beyond the visible components, affecting how galaxies like the Milky Way evolve over cosmic time. By studying the halo, astronomers are piecing together a clearer picture of the Milky Way's history. Moreover, these investigations provide crucial insights into the broader cosmic environment in which our galaxy resides. As new observational techniques and data continue to emerge, our understanding of the Milky Way and the mysteries within it continues to expand. Galaxies like the Milky Way are not static entities. Their formation and evolution are intricate processes that unfold over billions of years, beginning with the birth of the universe. In the aftermath of the Big Bang, the universe was a hot, turbulent expanse of particles that gradually cooled and began to clump together under gravity. These early fluctuations in density led to the formation of the first stars, which in turn gave birth to the first galaxies. As these primordial galaxies formed, they began interacting and merging with one another. This process of merging is crucial to the growth of galaxies, with smaller galaxies combining to form larger, more complex structures. During these mergers, gas is funneled toward the galactic center, igniting intense bursts of star formation. These explosive events are often accompanied by the creation of supermassive black holes in the galaxy's core, beasts of gravity that play a pivotal role in the galaxy's ongoing evolution. Through time, galaxies like the Milky Way pass through various stages of development. Factors such as star formation rates, supernovae, and the accretion of gas and dark matter continuously shape these galaxies. As stars live out their lifespans and die, they enrich the interstellar medium with heavy elements through violent supernova explosions. This process of enrichment fosters the creation of new stars and contributes to the formation of distinct components within the galaxy, such as the central bulge, the disk, and the halo. Galaxies are not isolated objects. They are constantly interacting with their environments, and these interactions can have a profound impact on their evolution. The Milky Way, for example, resides within a larger structure called the local group, where it regularly interacts with nearby galaxies. These encounters can trigger new waves of star formation, alter the shape of galaxies, and even set the stage for future mergers. Over cosmic timescales, the interplay between formation, evolution, and environmental factors allows galaxies to continuously evolve, altering their appearance and characteristics. Ultimately, these changes influence not only the structure of individual galaxies, but also the broader structure of the universe itself. As we study the formation of galaxies, we uncover the dynamic history of the Milky Way and its evolution into the grand spiral galaxy we recognize today. Nebulae are among the most captivating objects in the universe, serving as both markers of star formation and indicators of the life cycle of matter in the Milky Way. These cloud-like structures are diverse in nature, each playing a unique role in the cosmic environment. One of the most famous types is the emission nebula, which glows brightly due to the ionization of gas by nearby hot young stars. When ultraviolet light from these stars ionizes the hydrogen gas, it emits light at specific wavelengths, producing stunning colors, often shades of red and pink. The Orion Nebula is a prime example, offering a vivid view of ongoing star formation. In contrast, reflection nebulae do not emit light on their own. Instead, they reflect the light of nearby stars. These nebulae often appear blue because blue light scatters more efficiently than red. These nebulae typically surround young stars that have not yet ionized their surrounding material. A well-known example of this phenomenon is the nebula surrounding the star Rho Ophiuchi, where the stark contrast between bright stars and the surrounding dust creates a breathtaking scene. Dark nebulae, on the other hand, are dense clouds of gas and dust that block the light from stars and other objects behind them. These regions are often seen as dark silhouettes against the backdrop of brighter stars or emission nebula. One of the most famous dark nebula, the Horsehead Nebula, showcases how these opaque clouds obscure light while harboring the potential for future star formation within their depths. Planetary nebulae represent a significant chapter in the life cycle of stars, particularly those of medium size. As these stars exhaust their nuclear fuel, they expel their outer layers, creating a glowing shell of ionized gas that surrounds the remnant core. The Ring Nebula stands as one of the most iconic examples of this phenomenon, providing a striking illustration of the transition a star undergoes before its ultimate fade into the cosmos. These nebulae are more than just beautiful remnants. They are vital to our understanding of stellar evolution, the ongoing transformation of matter in space, and the broader mechanisms that shape the universe. Each type of nebula offers insight into the dynamic processes within our galaxy, revealing the delicate dance of birth, transformation, and death that stars undergo. At the heart of this celestial activity lies the interstellar medium, the vast, diffuse expanse of matter that fills the space between stars in a galaxy. Composed primarily of gas and dust, the interstellar medium consists mostly of hydrogen, about 75%, and helium, about 25%, with trace amounts of heavier elements like carbon, nitrogen, and oxygen. The dust particles embedded within this medium play an essential role by absorbing and scattering light, which in turn affects how we observe nebulae and other astronomical phenomena. This interstellar medium isn't a static backdrop. It is a crucial participant in the creation and transformation of stars. When certain regions of this medium experience changes in density, often triggered by gravitational instabilities or shock waves from nearby supernova, they can form dense molecular clouds. These clouds, often referred to as stellar nurseries, are rich in gas and dust, providing the essential materials needed to create new stars. Within these molecular clouds, gravity causes the gas and dust to compress, forming clumps that can eventually give birth to individual stars. As the material within these clumps continues to collapse, the pressure and temperature rise dramatically. Once the conditions are just right, nuclear fusion ignites, marking the birth of a new star. This chain of events illustrates how the interstellar medium is much more than a mere backdrop. It is a key actor in the ongoing story of the galaxy's evolution. Even after stars are born, the interstellar medium remains a dynamic player in the cycle of stellar life and death. When stars reach the end of their lives and explode as supernova, they release vast amounts of energy and material back into the interstellar medium, enriching it with heavier elements. This continuous cycle of star birth, death, and material recycling is crucial for the ongoing evolution of galaxies, providing the raw materials necessary for the formation of new stars. By studying the interstellar medium and its influence on star formation, astronomers are piecing together the intricate history of galaxies like the Milky Way. These discoveries shed light on the interconnectedness of cosmic phenomena, helping to explain how the universe continues to evolve. The interstellar medium, with its vast regions of gas and dust, plays a central role in the grand tapestry of the cosmos. To unlock the secrets of stars and nebulae, astronomers have developed several sophisticated techniques, with spectroscopy standing at the forefront. Spectroscopy involves splitting light into its component wavelengths using a device called a spectroscope. This technique allows astronomers to identify specific lines in the spectrum of light emitted or absorbed by a star or nebula, revealing the fingerprints of various elements and molecules present. For example, each element in the universe emits light at specific wavelengths, much like a barcode. The spectral lines corresponding to these wavelengths allow astronomers to determine which elements are present in a star or nebula. The distinctive lines of hydrogen, for instance, can be easily identified, while the presence of heavier elements, such as carbon and oxygen, can also be deduced through this method. By analyzing these spectral patterns, astronomers can infer critical information about the chemical composition, temperature, density, and other physical properties of celestial objects, providing clues about their formation and evolution. In addition to spectroscopy, astronomers also use photometry to study stars. Photometry involves measuring the intensity of light emitted by a celestial object at different wavelengths. By analyzing the light curves produced through this method, astronomers can gather valuable information about a star's temperature, size, and other characteristics, as different temperatures correlate with specific colors of light. When combined with spectroscopic data, photometry provides a more complete picture of a star's properties, helping scientists piece together the complex story of its life. Through these methods, astronomers continue to deepen our understanding of the cosmos, using light as a tool to unlock the mysteries of stellar formation, evolution, and the intricate processes that shape the universe itself. Advancements in technology, particularly the development of space-based observatories, have dramatically expanded our ability to explore the vast cosmos. These instruments enable us to study celestial objects across a wide range of wavelengths: ultraviolet, infrared, and radio. Each of these wavelengths offers a unique window into the universe, revealing the hidden compositions and behaviors of stars and nebulae. For example, infrared observations can penetrate dense clouds of cosmic dust, allowing astronomers to peer into regions of star formation that are typically obscured in optical wavelengths. By combining data from multiple observational methods, scientists continue to peel back the layers of complexity that define our universe. The study of stellar and nebular composition not only deepens our understanding of individual celestial objects, but also provides vital clues about the larger processes that govern galaxy formation, chemical evolution, and the intricate life cycle of matter in space. At the heart of these processes lie stellar nurseries, vast regions in space where new stars are born. These nurseries are often found within molecular clouds, dense formations of gas and dust that serve as the primary breeding grounds for stars in our Milky Way galaxy. Under the influence of gravity, these clouds condense and collapse, creating the perfect conditions for the formation of protostars. Over time, these protostars evolve into fully fledged stars, contributing to the ever-continuing cycle of stellar birth in the galaxy. Within the Milky Way, stellar nurseries are scattered across different regions, particularly in the spiral arms, where the density of gas and dust is higher. One of the most well-known examples is the Orion Nebula, located in the Orion constellation. This nebula is easily visible to the naked eye and serves as a vibrant laboratory for studying star formation in real time. It is teeming with young luminous stars and provides a prime environment for protostars to develop. Another significant stellar nursery is the Lagoon Nebula, situated in the constellation Sagittarius. This region is not only home to ongoing star formation, but also hosts a number of young star clusters. Similarly, the Carina Nebula, located in the southern sky, showcases an impressive number of newly formed stars, including some of the most massive stars known to humanity. Stellar nurseries can also be found in association with giant molecular clouds scattered across the galaxy. These clouds are often located in regions of active star formation, such as the dense cores of spiral arms, or in areas influenced by previous stellar activity, including supernova explosions. The interactions between stars and the interstellar medium in these environments help create the conditions necessary for future generations of stars to form. Understanding these stellar nurseries is crucial for unlocking the mysteries of stellar life cycles, the formation of planetary systems, and the broader evolution of galaxies. Supermassive black holes, immense gravitational giants found at the centers of most large galaxies, including our own Milky Way, play a profound role in shaping the evolution of their host galaxies. These black holes can have masses ranging from millions to billions of times that of the Sun, and their influence extends far beyond their immediate vicinity, affecting star formation, galaxy structure, and even the overall dynamics of entire galactic systems. One of the primary ways supermassive black holes impact galactic evolution is through feedback mechanisms. As material such as gas and dust falls toward the black hole, it forms an accretion disk, a disk of intensely hot and energetic material spiraling inward. The enormous gravitational forces exerted by the black hole, along with the energy released in the form of radiation, can produce powerful outflows and jets. These energetic bursts of radiation and particles can heat up surrounding gas, preventing it from collapsing to form new stars. In this way, supermassive black holes regulate the rate of star formation in their galaxies, ultimately shaping their evolution and star formation histories. When we look at the heart of a galaxy, we find something truly extraordinary: supermassive black holes. These cosmic giants don't just sit silently at the center. They play a dynamic and crucial role in shaping the very fabric of their host galaxies. Their gravitational influence extends far beyond their immediate vicinity, affecting the orbits of nearby stars and gas. This gravitational pull can lead to complex interactions, with stars being drawn into stable orbits around the black hole, eventually forming a central cluster. Through these interactions, the supermassive black hole helps maintain the structure of the galaxy's core. Moreover, the growth and evolution of supermassive black holes are intimately connected with the evolution of their galaxies. As galaxies merge, their central black holes move closer together, eventually merging into one massive black hole. This cosmic merger can have dramatic effects on the surrounding galactic environment. The process often triggers bursts of star formation, reshaping the overall morphology of the galaxies involved. But there's more. The presence of a supermassive black hole can also influence the distribution of dark matter within the galaxy. It shapes the way dark matter halos evolve and interact with visible matter, altering the gravitational landscape of the entire galaxy. These interactions are fundamental to the development of galaxies as we know them. Studying supermassive black holes is therefore essential to understanding the broader processes that govern galaxy formation and evolution. These entities are not just the final stage of stellar life. They are active participants in the complex dance of cosmic evolution, influencing the fate of galaxies and their central cores. Galaxy mergers are one of the most captivating events in the universe. When two or more galaxies collide, they undergo a transformative process under the pull of their mutual gravity. These mergers can range from the collision of small dwarf galaxies with larger ones to massive, dramatic interactions between giant spiral galaxies. The merging process unfolds over millions to billions of years, leading to profound changes in the structure and composition of the galaxies involved. The Milky Way, for instance, is on a collision course with the Andromeda Galaxy, the nearest spiral galaxy. This cosmic collision is expected to take place in about 4 billion years and will reshape the future of both galaxies. The gravitational interactions between the two will likely trigger bursts of star formation, compressing gas and dust as their interstellar media collide. In these regions of intense interaction, new stars may be born. However, despite the chaos of the merger, the stars themselves are unlikely to collide, thanks to the vast distances that separate them. These galactic mergers are not just events of destruction. They are the crucible for creating new stars, reshaping galaxies, and advancing the cosmic cycle of evolution. However, their orbits will be profoundly affected, potentially leading to the creation of new galactic structures. The Milky Way and Andromeda are likely to lose their distinct identities, eventually merging into a new elliptical galaxy. Over time, this cosmic collision will also lead to the formation of a supermassive black hole at the center of the newly formed galaxy. The black holes at the heart of each original galaxy will draw together, merging and coalescing into a singular massive entity. As this process unfolds, the distribution of dark matter will be reconfigured, reshaping the gravitational landscape within the newly formed galaxy. This restructuring could influence the orbits of remaining stars, alter dark matter distribution, and even lead to the formation of new galactic subsections or structures, such as tidal tail streams of stars and gas extending outward from the merging galaxies. While this cosmic collision may seem catastrophic, it is part of the natural cycle of galaxy evolution. Understanding galaxy mergers gives astronomers valuable insights into how galaxies grow and evolve over cosmic timescales. The Milky Way's impending merger with Andromeda serves as a reminder of our galaxy's dynamic nature and the continuous processes that shape the universe. It illustrates that even colossal systems are subject to change and transformation as they traverse the cosmic landscape. Gamma-ray bursts are among the most powerful and energetic explosions observed in the universe, releasing immense amounts of energy in the form of gamma rays. These bursts can last from a fraction of a second to several minutes, and are believed to originate from two primary types of astronomical events: the collapse of massive stars into black holes, often accompanied by supernova, and the merger of binary neutron stars, or neutron-star black hole systems. The intense energy emitted during a gamma-ray burst can have profound effects on its surrounding environment. When a burst occurs, the gamma rays travel vast distances through space, and if they are directed toward a galaxy, they can impact the interstellar medium. This impact can ionize gas, compress surrounding material, and trigger waves of star formation by compressing gas clouds into regions where new stars can form. One of the most dramatic potential effects of a gamma-ray burst is its capacity to irradiate nearby stars and planets. If a gamma-ray burst were to occur close to our galaxy, within a few thousand light years, it could expose the outer layers of nearby celestial bodies to harmful radiation. This radiation could severely impact any existing life forms or disrupt the atmospheric chemistry of planets, potentially leading to mass extinctions or altering biospheres. Moreover, frequent gamma-ray bursts occurring in a galaxy's history might indicate regions of active star formation and cosmic arms. Their study helps astronomers understand the conditions that lead to extreme stellar evolution and provides insight into the processes that shape galactic dynamics. Gamma-ray bursts serve as cosmic beacons, highlighting the violent and dynamic nature of the universe. By studying these phenomena, astronomers can gain valuable knowledge about the life cycles of massive stars, the behavior of extreme conditions, and the complex interactions occurring within galaxies. Understanding these bursts also sheds light on the potential impact of such extraordinary events on the history and evolution of galaxies, including our own Milky Way. Supernovae are explosive events marking the death of massive stars, and they play a crucial role in the evolution of the Milky Way. As these stars reach the end of their life cycles, they expel their outer layers into space with tremendous force, creating shockwaves that significantly impact their surroundings. Supernovae contribute to the galactic ecosystem in several vital ways. One primary effect of supernovae is the enrichment of the interstellar medium with heavy elements. During their life cycles, massive stars forge elements like carbon, oxygen, and iron through nuclear fusion. When a supernova occurs, these elements are released into the surrounding gas and dust, enriching the interstellar medium. This process of chemical enrichment is fundamental for subsequent generations of stars, as it allows for the formation of planets and the building blocks of life. Without the contributions from supernovae, the universe's elemental diversity would be severely limited. Furthermore, the shock waves generated by supernova explosions can trigger new star formation. As the expelled material collides with surrounding gas clouds, it compresses them, increasing their density. This can lead to the collapse of these clouds and the birth of new stars. In this way, supernovae act as agents of stellar recycling, fostering the continuous cycle of star formation within the Milky Way. Supernovae also influence the dynamics and structure of the galaxy. The energy released during an explosion can create supernova remnants, often observed as nebulae of glowing gas and dust. These remnants can cause turbulence within the interstellar medium, affecting how gas moves and flows throughout the galaxy. This turbulence, in turn, can impact the gravitational interactions within the Milky Way, gradually shaping its overall structure over time. Supernovae play a crucial role in shaping the fate of star clusters. When a massive star in a cluster explodes, the dynamics of the remaining stars can be dramatically altered, potentially disrupting the entire cluster. These explosive events can intensify gravitational interactions within the cluster, driving significant changes in its long-term evolution. Supernovae are vital contributors to the Milky Way's story, enriching the interstellar medium with essential elements, triggering new star formation, and influencing the galaxy's structure and dynamics. Their impact is fundamental to understanding the ongoing processes that shape our galaxy, illustrating the interconnectedness of stellar life cycles and the broader cosmic environment. Magnetars, a type of neutron star, stand as some of the most extreme objects in the universe due to their intensely powerful magnetic fields and enormous energy output. A neutron star is the collapsed remnant of a massive star that has exploded in a supernova. Under the crushing force of gravity, protons and electrons combine to form neutrons. Magnetars, however, take this extreme state further. These neutron stars possess magnetic fields about 1,000 times stronger than an ordinary neutron star and up to 1 trillion times stronger than Earth's magnetic field. The intense magnetic fields of magnetars govern their behavior and observable phenomena, creating extreme conditions that result in the release of energy in the form of soft gamma-ray bursts and X-rays. This activity is believed to stem from the decay of the magnetar's magnetic field over time, generating vast amounts of energy and emitting radiation that can be detected across enormous distances in space. Moreover, the magnetic fields of magnetars can profoundly impact their surroundings. The extreme magnetic environment can distort the structure of nearby materials, affecting the dynamics of surrounding star systems and the interstellar medium. If a magnetar is near other stars or planets, its intense radiation and magnetic forces can ionize nearby gases or even strip away atmospheres, significantly altering the potential for habitability. The extreme nature of magnetars makes them key objects of scientific study. Their unique properties challenge our understanding of stellar evolution, magnetic fields, and the fundamental laws of physics that govern the universe. By studying magnetars, researchers can gain valuable insights into the processes that lead to the formation of these extraordinary objects and the role they play in the broader astrophysical context. Magnetars showcase the fascinating diversity of celestial phenomena, pushing the boundaries of our understanding of the cosmos and highlighting the need for continued exploration in unraveling the mysteries of cosmic evolution. Cosmic rays are high-energy particles that travel through space, reaching Earth from various energetic sources. Primarily originating from supernova, active galactic nuclei, and other intense astrophysical processes, these rays are mostly composed of protons, though they can also include heavier nuclei, electrons, and even photons. Understanding their origins and the way they traverse the galaxy provides crucial insights into high-energy astrophysics and the dynamics of the universe. The leading source of cosmic rays is believed to be the explosive deaths of massive stars in supernovae. When these stars exhaust their nuclear fuel and explode, they generate shock waves that accelerate charged particles to extraordinary speeds. These particles can acquire energies far greater than those produced in human-made particle accelerators. As supernova remnants expand, they create turbulent environments where particles gain energy through interactions with shock waves and magnetic fields. Another significant source of cosmic rays comes from active galactic nuclei, the regions surrounding supermassive black holes at the centers of galaxies. As matter falls toward these black holes, it accelerates, emitting radiation across multiple wavelengths. The energetic processes in these regions can also produce high-energy particles that escape into intergalactic space and enter our galaxy. Once generated, cosmic rays travel through the galaxy, their journey heavily influenced by the magnetic fields in the interstellar medium. These magnetic fields cause the particles to follow curved paths, making it challenging to trace their origins. As cosmic rays travel, they interact with the gas and dust in the interstellar medium, generating secondary particles like pions and kaons, which can cascade into even lower energy particles. Cosmic rays can take tens of thousands of years to travel from their origins to our solar system. Along the way, they may encounter regions with varying magnetic field strengths and densities, scattering and diffusing as they move. Despite these interactions, about 1% of cosmic rays manage to reach Earth, where they can be detected by ground-based observatories and high-altitude balloon experiments. Studying cosmic rays allows scientists to probe not only the distant cosmic events that produce them, but also the underlying mechanisms of particle acceleration and propagation in the galaxy. Understanding high-energy particles offers us a glimpse into the extreme environments and phenomena that define the universe, enriching our comprehension of the complex interactions between cosmic forces and the very structure of our galaxy. These particles provide critical insights into the forces at play in the most violent and remote corners of space. Gravitational waves, the ripples in the fabric of space-time, emerge when massive objects like black holes or neutron stars accelerate. Picture this. If you were to throw a stone into a calm pond, the ripples that spread across the surface would be the equivalent of gravitational waves, traveling outward across the universe. These waves carry precious information about their origins and the nature of gravity itself, offering an entirely new way to observe celestial events. The concept of gravitational waves was first proposed by Albert Einstein over a century ago as part of his groundbreaking general theory of relativity. This theory fundamentally altered our understanding of gravity, not as a force, but as the bending of space-time caused by mass. However, it wasn't until 2015 that the Laser Interferometer Gravitational Wave Observatory, LIGO, made history with the first direct detection of gravitational waves, confirming their existence and opening an unprecedented window into the cosmos. With the ability to detect these waves, scientists have been able to observe cosmic phenomena that were once invisible to us. One of the most significant discoveries came from the merging of black holes, events so massive and energetic that they emit gravitational waves that carry details about the objects involved, details that would have been entirely inaccessible through traditional telescopes. These findings allow physicists to challenge existing theories of spacetime and fundamental forces. But the story doesn't end there. Gravitational waves have also provided direct evidence for neutron-star mergers, unveiling new insights into the formation of heavy elements like gold and platinum in the universe. As our detection methods continue to improve, we are only scratching the surface of the hidden workings of the universe. Each new discovery peels back another layer, helping us better understand the intricate astrophysical processes that shape the cosmos. Cosmic inflation, the theory that the universe expanded at an astonishing rate immediately following the Big Bang, further deepens our understanding of the universe's early moments. This expansion, which occurred in a fraction of a second, roughly between 10 to the power of minus 36 seconds and 10 to the power of minus 33 seconds after the universe's birth, was far more rapid than anything observed under normal circumstances. It was during this brief but monumental period that the structure of the cosmos began to take shape. Inflation was proposed to solve several perplexing issues in cosmology, such as why the universe appears so flat and homogeneous across vast distances. Before this theory, these characteristics posed significant challenges. The inflationary period stretched quantum fluctuations, minute variations in energy, across unimaginable distances, setting the stage for the density differences that would eventually form galaxies and clusters of galaxies. The theory of inflation serves as a bridge between the universe's earliest moments and the observable cosmos we see today. As the universe expanded, it also cooled, allowing for the formation of fundamental particles, which eventually came together to form atoms, stars, galaxies, and more. Inflation helps us connect the microscopic quantum world with the macroscopic universe, showing how small, almost imperceptible fluctuations led to the grand structures we now observe in the universe. Crucially, observations of the cosmic microwave background radiation, the afterglow of the Big Bang, provide strong evidence for inflation. This radiation carries imprints of the universe's early conditions, and the temperature fluctuations observed in this relic radiation closely match the predictions made by inflationary models, reinforcing the theory's validity and role in understanding the universe's evolution. Through the lens of cosmic inflation, we unlock profound insights into the origins and evolution of the universe as we know it. The study of dark energy, the mysterious force believed to be responsible for the accelerated expansion of the universe, has become a central focus for astronomers. By employing various observational techniques, one of the most reliable tools at their disposal is the analysis of light from distant supernovae, particularly type 1a supernovae. These explosive events occur in binary star systems when a white dwarf star accumulates material from a companion star until it reaches a critical mass, resulting in a powerful explosion. Because type 1a supernovae have a consistent peak luminosity, they act as reliable standard candles. By measuring their brightness and redshift, astronomers can accurately gauge their distance from Earth and track the universe's expansion rate, providing a valuable tool for studying dark energy and the accelerating growth of the cosmos. Astronomers observe the large-scale structure of the universe, which includes galaxy clusters and the cosmic web formed by the distribution of galaxies. By mapping the arrangements and movements of galaxies, scientists can infer the influence of dark energy on cosmic acceleration. Comparing the observed structure of the universe with simulations allows them to gauge how dark energy affects gravitational dynamics and galaxy formation over time. Another critical approach in this cosmic investigation involves studying the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation holds crucial clues about the universe's expansion history. Precise measurements of temperature fluctuations within this radiation can provide valuable insights into the density, and distribution of both matter and dark energy across the cosmos. Missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have contributed immensely, offering detailed data that helps astronomers understand how dark energy influenced the early universe's evolution. By combining these techniques, astronomers are gradually piecing together a comprehensive understanding of dark energy's role in galactic expansion. The effect of dark energy on the cosmos is profound, as it constitutes approximately 70% of the universe. Each discovery not only advances our knowledge of this mysterious force, but also enhances our understanding of fundamental physics and the ultimate fate of the universe. Quasars, or quasi-stellar objects, are incredibly luminous and distant celestial phenomena powered by supermassive black holes at the centers of galaxies. These black holes, often millions or even billions of times more massive than our Sun, generate immense amounts of energy as matter falls into them, forming an accretion disk. The energy released from this disk results in brightness far exceeding their host galaxies. This extraordinary luminosity makes quasars visible over vast distances, allowing them to serve as beacons for studying the universe's evolution. Quasars were most prevalent during a period known as cosmic noon, roughly between 10 and 12 billion years ago, when the universe was much younger. During this epoch, many galaxies were in the process of significant formation and growth, frequently merging with one another. The increased interactions between galaxies, along with the inflow of gas and dust into the central supermassive black holes, likely triggered quasar activity. Studying quasars offers astronomers a glimpse into the conditions that fostered galaxy evolution. Quasars provide essential insights into the formative processes of galaxies. The energetic outflows and jets produced by material falling into black holes can significantly influence star formation, either suppressing it by heating surrounding gas or triggering new star formation by compressing it. This feedback mechanism highlights the delicate balance between a galaxy's growth and the influence of its central black hole. The study of quasars also raises intriguing questions about the relationship between galaxy formation and black hole growth. Understanding how these powerful entities evolve together offers crucial clues about the history of the universe and the mechanisms driving cosmic structure formation. As astronomers continue to explore these brilliant beacons, quasars remain central to unraveling the mysteries of galactic evolution and the dynamic processes that shape the cosmos. Black holes exert a profound influence on the fabric of spacetime within galaxies. Their immense mass and gravitational pull cause a significant warping of the surrounding spacetime, which profoundly impacts the motion of nearby stars, gas, and dust. According to Einstein's general theory of relativity, gravity is not simply a force, but a curvature in spacetime around massive objects. A black hole, with its concentrated mass, often millions or even billions of times that of the Sun, creates a gravitational well that affects the orbits and trajectories of nearby objects. As objects come close to a black hole, they experience stronger gravitational forces, altering their orbits and paths. This interaction leads to complex dynamics, especially in the dense cores of galaxies. Stars can be pulled toward a black hole, eventually spiraling in and becoming part of the accretion disk. However, the gravitational influence of black holes can also result in the ejection of stars from the galaxy into intergalactic space, a phenomenon known as the gravitational slingshot effect. This complex and fascinating relationship between black holes and their surrounding galaxies shapes the very structure of the cosmos. Moreover, black holes play a crucial role in the evolution of their host galaxies through various feedback mechanisms. For example, the energy released when material is pulled into a black hole can drive powerful outflows in jets. These jets can heat the surrounding gas or even expel it entirely, preventing it from cooling and collapsing to form new stars. This feedback process illustrates how black holes can regulate star formation on a galactic scale. The study of black holes also deepens our understanding of gravitational waves, particularly during cosmic events like mergers. When two black holes collide, they generate gravitational waves that ripple through the fabric of space-time, offering invaluable insight into the nature of these enigmatic entities and their role within galaxies. This expanding knowledge not only enhances our comprehension of the complexities of space-time, but also underscores the integral role black holes play in shaping the universe's structure and evolution. Within our own Milky Way galaxy, we witness an array of energetic events that highlight the dynamic nature of cosmic processes. Among the most dramatic are supernovae, the explosive deaths of massive stars. These awe-inspiring events release an amount of energy equivalent to that of an entire galaxy, but in a fraction of the time. When a massive star exhausts its nuclear fuel, it can no longer resist the pull of gravity, leading to a cataclysmic explosion that sends its outer layers hurtling into space at immense velocities. Supernovae not only enrich the interstellar medium with heavy elements, but they also trigger star formation in nearby regions by compressing gas and dust. Another significant phenomenon within our galaxy is the occurrence of gamma-ray bursts, some of the most powerful explosions in the universe. These bursts are linked to the collapse of massive stars or the merger of compact objects, like neutron stars. When these events unfold, they release intense beams of gamma rays, observable across vast cosmic distances. While gamma-ray bursts are often distant events, their detection within our own galaxy would signal an extraordinary level of cosmic activity, sending shockwaves through the very fabric of the universe itself. As matter spirals toward the supermassive black hole at the heart of the Milky Way, known as Sagittarius I, an extraordinary spectacle of energy unfolds. This is not merely a cosmic curiosity, it is a violent and intense phenomenon. When gas clouds collide with Sagittarius A star, they release flares of energy that ripple across the universe in bursts of radiation. These flares, accompanied by intense X-rays and other wavelengths, illustrate the chaotic power of black hole dynamics. The very act of matter being drawn into the abyss generates energy on a scale that is hard to fathom, 10 to the power of 26 times the energy output of our sun. This immense activity is not isolated. High-energy cosmic rays, generated by the violent interactions between particles and the interstellar medium, travel throughout the galaxy, scattering bursts of radiation in their wake. These interactions are more than just chaotic events. They are key pieces in the puzzle of how galaxies evolve. By observing these cosmic explosions and energetic bursts, scientists gain crucial insights into the forces that shape not just the Milky Way, but the very fabric of the universe. The violent events of the Milky Way reach beyond its own boundaries, with neighboring galaxies also contributing to our understanding of cosmic forces. The Milky Way's closest galactic neighbors belong to a collection known as the Local Group, a grouping of more than 50 galaxies bound together by gravity. This collection includes some truly spectacular members, such as the Andromeda Galaxy and the Triangulum Galaxy. Andromeda, located 2.5 million light-years away, is the closest spiral galaxy to the Milky Way. With a staggering 1 trillion stars, Andromeda is not only a beautiful galaxy in its own right, but also a reminder of the future collision that awaits our galaxy. The Milky Way and Andromeda are on a collision course, a cosmic event that will unfold over the next 4 billion years, ultimately merging both galaxies into a new, combined entity. Another notable member of the Local Group is the Triangulum Galaxy, a striking spiral galaxy situated roughly 3 million light-years from Earth. Triangulum is the third largest member of the group and, like the Milky Way, features magnificent spiral arms and hundreds of millions of stars. The study of Triangulum offers valuable clues about how galaxies form and evolve. giving researchers insight into the processes that drive the growth and transformation of galaxies over time. In addition to these larger, more prominent galaxies, the local group also includes several dwarf galaxies, such as the Large and Small Magellanic Clouds. These irregular galaxies, orbiting the Milky Way from distances of approximately 160,000 and 200,000 light years, respectively, are pivotal for understanding galaxy interactions. Their influence on the Milky Way's evolution, particularly in terms of star formation and gravitational interactions, is significant. These smaller galaxies offer a fascinating glimpse into how even the smallest members of the cosmic family can shape the dynamics of the larger, more massive galaxies. The interplay between the Milky Way and its nearby galaxies is not just about their individual evolution, but about the way galaxies influence one another over time. Whether through gravitational interactions, star formation, or eventual mergers, the future of the Milky Way will continue to be shaped by its interactions with these neighboring galaxies. This interconnectedness, woven through the fabric of the cosmos, reminds us that no galaxy exists in isolation. Each one, no matter how far or near, is part of a vast and ever-expanding universe, where the fate of one can influence the destiny of many. The local group is home to a variety of dwarf galaxies that contribute to the intricate tapestry of our cosmic neighborhood. Among the most notable are the Fornax dwarf, the Carina dwarf, and the Sculptor dwarf, each adding to the diversity and richness of the group. These small galaxies play a significant role in the study of galaxy formation and evolution, offering a unique lens through which astronomers explore the forces that shape galaxies and bind them together. The interactions between these galaxies provide valuable insights into the gravitational forces that govern their behavior, making the local group an essential focus for understanding the larger universe. At the heart of the local group lies a fascinating comparison: the Andromeda Galaxy, also known as M31, and our own Milky Way. These two massive spiral galaxies, often considered the closest counterparts in our cosmic neighborhood, share several striking similarities, yet also boast some intriguing differences. One of the most notable distinctions is their size. Andromeda is slightly larger than the Milky Way, containing about 1 trillion stars compared to the Milky Way's estimated 200 to 400 billion. This makes Andromeda the largest galaxy in the local group, with the Milky Way coming in second. Both galaxies exhibit the classic spiral structure, with winding arms filled with stars, gas, and dust. Andromeda's spiral arms are well-defined, serving as hubs of active star formation. The Milky Way shares this feature, though some of its spiral structures are obscured by the interstellar dust that clouds our view. Observations across infrared and other wavelengths have allowed astronomers to peer through this dust, revealing the full extent of our galaxy's spiral features. The presence of these arms in both galaxies indicates a long history of star formation, though the rate at which new stars are born may differ between them. Another fascinating difference between these two giants lies in the supermassive black holes at their centers. The Milky Way hosts a black hole known as Sagittarius A Sti, while Andromeda's center contains a more massive black hole, sometimes referred to as M31 star. These black holes are not mere cosmic curiosities. They have a profound impact on the dynamics of their respective galaxies. Observations of Andromeda's black hole suggest that it is more active than Sagittarius A Sti, and this activity could play a role in influencing the rate of star formation within the galaxy, as well as its overall evolution. Looking into the future, Andromeda and the Milky Way are on a collision course. In about 4 billion years, these two galaxies are predicted to merge, offering astronomers a rare opportunity to study the processes that govern galactic interactions. This event will create a new galaxy, offering deeper insights into the gravitational forces and stellar evolution that occur over vast cosmic timescales. The impending merger stands as a testament to the dynamic and evolving nature of galaxies in the universe. In addition to the larger galaxies of the local group, satellite galaxies also play a crucial role in shaping the overall structure and dynamics of the group. These smaller galaxies orbit around larger, more massive galaxies like the Milky Way and are bound by their gravitational pull. Over time, the interactions between the satellite and the larger galaxy can significantly alter the satellite's trajectory, morphology, and even its internal structure. Tidal forces, for example, can strip gas from the satellite, affecting its ability to form new stars and shaping its overall appearance. The Milky Way is surrounded by several prominent satellite galaxies, with the large and small Magellanic Clouds being the most well-known. These irregular galaxies, located roughly 60,000 and 200,000 light-years away, are easily visible from the southern hemisphere and offer astronomers a fascinating window into star formation and galactic dynamics. In addition to the Magellanic Clouds, several other satellite galaxies are confirmed to be orbiting the Milky Way, including the Fornax Dwarf, Carina Dwarf, Sculptor Dwarf, and Leo 1. Altogether, there are around 30 known satellite galaxies, though astronomers believe that many more may yet be discovered. As our understanding of the local group continues to grow, these small galaxies will remain essential to the study of galaxy formation, evolution, and the complex interactions that govern our universe. Each new discovery brings us one step closer to unraveling the mysteries of our cosmic neighborhood. Satellite galaxies play a critical role in shaping our understanding of galaxy formation and evolution. Observing how these smaller galaxies interact with the Milky Way opens a window into the complex processes that govern galaxy dynamics, star formation, and gravitational interactions. These interactions also offer valuable insights into dark matter, as the behavior of satellite galaxies provides essential clues about mass distribution throughout the universe. Galaxies interact with one another through the immense force of gravity, triggering a variety of phenomena that can significantly alter their structure and star formation rates. When two galaxies approach one another, their gravitational fields begin to exert powerful forces on each other. This often leads to tidal forces, variations in the gravitational pull that different parts of the galaxies experience. These tidal forces can stretch and distort the galaxy's shapes, sometimes forming elongated structures or tidal tails that can stretch for hundreds of thousands of light years. As galaxies draw closer, these gravitational interactions can spark bursts of new star formation. The immense gravitational pull can compress gas and dust within the galaxies, increasing the density in certain regions. This compression can trigger the collapse of gas into new stars, resulting in vibrant starburst activity. Such events provide fertile ground for the creation of new stars while reshaping the existing stellar populations. In some cases, when galaxies interact closely enough, they can merge to form larger galaxies. During a merger, the gravitational forces may cause gas to flow toward the centers of the galaxies, fueling active galactic nuclei, or even activating supermassive black holes at their cores. The outcome of these mergers depends on the mass and type of the interacting galaxies. Mergers can range from complete coalescence into a single, larger galaxy to the creation of a new galaxy with a completely different structure and composition. Gravitational interactions can also lead to the stripping of material from one galaxy to another, a process known as tidal stripping. In this scenario, a smaller galaxy loses gas, stars, or other material to a larger galaxy, which contributes to the growth of the more massive galaxy over cosmic timescales. These interactions are crucial in galaxy evolution, shaping the structure and distribution of galaxies across the universe and influencing their star formation histories. Evidence of past galactic mergers in the Milky Way's history can be found in a variety of ways. Observational data, such as the analysis of the galaxy's stellar population, its kinematics, and the structure of its halo, all point to the existence of ancient galactic interactions. One clear sign of past mergers is the presence of streams of stars and globular clusters that exhibit unusual orbits around the Milky Way. These tidal streams are remnants of smaller galaxies that were gravitationally disrupted and absorbed by the Milky Way over billions of years. For example, the Gaia sausage, a structure discovered through data from the Gaia Space Observatory, is thought to be the remnants of a disrupted dwarf galaxy. This long-lost galaxy contributed a significant number of stars to the Milky Way's halo, leaving behind a trace that can still be detected in the galaxy's stellar population today. Through these stellar relics, we gain a deeper understanding of the Milky Way's violent and dynamic past. revealing the complex cosmic ballet of galaxy interactions that have shaped our galaxy into what it is today. The chemical composition of stars holds crucial insights into the history of the Milky Way. As smaller galaxies collided with our galaxy, they brought with them unique blends of elements, enriching the Milky Way's stellar environment. This is reflected in the wide range of metallicities observed in stars. Metallicity refers to the abundance of elements heavier than hydrogen and helium. When we focus on certain stellar populations, particularly older stars in the halo and bulge, a fascinating pattern emerges. These stars show significantly different chemical signatures compared to those in the Milky Way's disk. This suggests that they are remnants of smaller galaxies that merged with our galaxy long ago. The timing and nature of these ancient mergers can be reconstructed using advanced simulations of galactic evolution. These models, based on the most recent simulations, provide a detailed picture of how the Milky Way formed and evolved over billions of years. In particular, they reveal that the Milky Way interacted with smaller galaxies most intensely between 6 and 10 billion years ago. This timeframe aligns with our understanding of galaxy formation in the early universe, supporting the idea that our galaxy's history is deeply intertwined with these cosmic encounters. The Milky Way, our home galaxy, is not an isolated entity in the vastness of space. Its interactions with satellite galaxies, like the Large and Small Magellanic Clouds, offer a fascinating window into the cosmic processes of accretion and galactic merging. These encounters are the echoes of the Milky Way's dynamic past, revealing how past events continue to shape its structure and evolution. By studying stellar dynamics, the chemical composition of stars, and using advanced computer simulations, scientists have been able to piece together the galaxy's rich and complex history, which has been shaped by numerous galactic mergers. One of the most captivating future events in our galaxy's timeline is the predicted collision between the Milky Way and the Andromeda Galaxy. This monumental event is set to unfold over the course of several billion years, but it's already underway. Both galaxies are moving toward each other at an astounding speed of about 100 kilometers per second, hurtling toward a collision that will come to a critical point in roughly 4 billion years. As the Milky Way and Andromeda approach one another, their gravitational interactions will trigger a cascade of effects, beginning with preliminary encounters that distort the galaxy's shapes. This first contact will ignite tidal forces, massive gravitational disruptions that will cause the galaxies to stretch and deform. It's likely that these tidal forces will also lead to dramatic bursts of star formation, as the gas clouds within the galaxies are compressed and triggered to collapse into new stars. As the two giants draw closer, the galaxies will form tidal tails, vast, streaming arcs of stars and gas that stretch out from their cores like cosmic tendrils reaching across the void. These tidal tails will be a striking testament to the power of gravitational forces at play. The true merger will unfold in several stages. After their initial close approach, the galaxies will exchange material and gravitational influence, spiraling around each other in a cosmic dance that could last hundreds of millions of years. Eventually, the galaxies will pass through one another, only to become gravitationally bound. From there, a prolonged merging process will begin, stretching over the course of 1 billion years or longer. Ultimately, the Milky Way and Andromeda will merge into a single larger galaxy, often referred to as Milkomeda or Mildrada. This new galactic entity will likely look very different from either of its parent galaxies. It may evolve into an elliptical galaxy with a smooth, featureless structure, as the merger smooths out the distinct spiral arms that currently define both the Milky Way and Andromeda. Despite the dramatic nature of these events, the vast distances between stars will ensure that direct collisions between individual stars are extremely rare. However, the gravitational interactions will reshape the galactic environment in profound ways. Star formation rates will shift, and the positions of stars will change as they are drawn into new orbits. The very fabric of both galaxies will be transformed as they are merged into a single new cosmic entity. These celestial events are part of the natural life cycle of galaxies. They highlight the ever-evolving and dynamic nature of the universe. The future merger between the Milky Way and Andromeda offers a glimpse into the ultimate fate of our galaxy, emphasizing how interconnected galaxies are in the vast cosmic web. Galactic cannibalism and harassment are two processes that describe how galaxies interact through the power of gravity, leading to significant structural and evolutionary changes. Galactic cannibalism occurs when a larger galaxy pulls in a smaller one, effectively absorbing it into its structure. The smaller galaxy is torn apart by the tidal forces of the larger one, losing stars, gas, and other materials as it is consumed. A prime example of this is the ongoing interaction between the Milky Way and its satellite galaxies, such as the Large and Small Magellanic Clouds. These smaller galaxies are slowly losing material to the Milky Way, being gradually consumed over time. On the other hand, galactic harassment happens when a smaller galaxy passes close to a larger one, experiencing intense gravitational forces that distort its shape and behavior. These interactions can compress gas clouds, triggering bursts of new star formation, or they can strip away stars and gas, weakening the smaller galaxy and making it more vulnerable to further gravitational interactions, or even eventual absorption by a larger galaxy. Both galactic cannibalism and harassment showcase the violent, dynamic nature of galaxy interactions. These phenomena contribute to our understanding of galaxy evolution, revealing how galaxies evolve through their gravitational relationships with one another and how these cosmic forces shape the universe as a whole. Between galaxies, vast intergalactic voids play a pivotal role in shaping the structure and evolution of the cosmos. These near-empty expanses, stretching millions of light years across, lie between clusters of galaxies, and though they may seem devoid of matter, their gravitational influence is profound. They significantly affect how galaxies move, interact, and evolve, providing crucial insights into the large-scale architecture of the universe. At first glance, the distribution of galaxies appears random, but in reality, it forms a complex, sponge-like structure known as the cosmic web. This web consists of dense clusters of galaxies, long filaments of dark matter and gas, and vast voids that weave together to create a vast cosmic network. Galaxies tend to concentrate in these filaments and clusters, while the voids, regions of very low matter density, serve as the space between. The gravitational forces within this structure are key drivers of galaxy formation. As galaxies journey through the universe, they don't move in isolation. Their paths are influenced by the gravitational pull of neighboring galaxies and structures. The voids, by creating large-scale pathways, can guide galaxies toward denser regions. This dynamic interaction shapes the trajectories of galaxies and can even lead to their eventual mergers. Interestingly, the presence of these voids impacts star formation within galaxies. Galaxies situated on the edges of voids often experience lower rates of star formation, primarily due to a lack of gas infall and interactions with other galaxies. In contrast, galaxies located within denser environments are more likely to experience bursts of star formation, often spurred by gravitational interactions with neighboring galaxies. These voids also reveal much about the early universe. The gravitational effects of the cosmic web leave traces in the cosmic microwave background radiation, the faint afterglow of the Big Bang. The uneven distribution of matter in the cosmic web contributes to subtle temperature fluctuations in this ancient light, offering scientists vital clues about the universe's infancy, the formation of galaxies, and the nature of dark matter. At the heart of this cosmic structure lie galaxy clusters, regions where galaxies are densely packed together. These clusters serve as essential nodes in the cosmic web, influencing the growth and evolution of galaxies through interactions such as mergers and the exchange of gas. As galaxies travel along filaments connecting these clusters, they accumulate mass and undergo complex evolutionary changes that are fundamental to the universe's grand design. The cosmic web also reflects the deeper laws of physics, connecting the dots between gravity, dark matter, and the forces that have sculpted the cosmos since its inception. As technology continues to advance, astronomers are uncovering ever more intricate layers of this vast network, revealing mysteries that challenge our understanding of the universe itself. In the midst of these cosmic processes, white dwarfs stand as poignant reminders of stellar life cycles. When stars similar in size to our sun reach the end of their lifespans, they shed their outer layers in a spectacular display known as a planetary nebula. What remains is a dense, hot core that eventually cools into a white dwarf. These remnants are incredibly compact, packing the mass of our Sun into a volume comparable to that of Earth. Over billions of years, a white dwarf will gradually cool and fade, offering astronomers crucial insights into the final stages of stellar evolution. They are the endpoint of low to medium mass stars, making them essential tools for understanding the life cycle of stars, and by extension, the forces that shape the universe. Through the study of these cosmic phenomena, voids, galaxy clusters, and white dwarfs, we gain invaluable knowledge about the forces that govern the universe, unveiling the intricacies of cosmic evolution and the enigmatic fabric that ties all things together. White dwarfs play a crucial role in our understanding of cosmic events. When a white dwarf is part of a binary system, it can gather matter from its companion star. This accumulation can result in dramatic outcomes. If the white dwarf collects enough mass, it may undergo a cataclysmic explosion called a supernova type 1a. This explosive event is not just a spectacular display of cosmic power, it serves as a vital tool for astronomers. The uniform brightness of these supernova allows scientists to measure cosmic distances with incredible accuracy, which has led to the groundbreaking discovery of the universe's accelerating expansion. Studying white dwarfs enriches our understanding of star formation and evolution, offering key insights into the development of the universe itself. As we observe these fascinating celestial objects, we are not just looking at their present state, we are peering into the past and future of the cosmos. In this way, white dwarfs become central players in the complex narrative of stellar evolution. Pulsars, on the other hand, are highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. These neutron stars are the remnants of a supernova explosion, where the core collapses under extreme pressure, forming a compact object of incredible density. In fact, a small chunk of neutron star material about the size of a sugar cube could weigh as much as a mountain. As a pulsar spins, the beam of radiation sweeps across the Earth. When it does, it is detected as pulses of radio waves, much like the flashing light from a lighthouse. These pulses occur at remarkably regular intervals, often ranging from milliseconds to several seconds. The precision of these pulses is one of the most striking features of pulsars. This regularity allows astronomers to use them as cosmic clocks, enabling them to measure time with astonishing accuracy. Pulsar observations provide crucial data about the star's rotation, magnetic field, and even the effects of relativistic physics in the vicinity of such massive objects. The most rapidly spinning pulsars, known as millisecond pulsars, can complete a rotation in just a few milliseconds. This demonstrates incredible kinetic stability. Pulsars are not just fascinating objects in their own right, they have profound implications for astrophysics. They are essential for testing fundamental theories of physics, including general relativity. In fact, the study of binary systems that contain pulsars has provided evidence for the existence of gravitational waves, ripples in spacetime caused by the acceleration of massive objects, as predicted by Einstein. Beyond this, pulsars serve as a tool for mapping the distribution of matter in our galaxy and beyond. By using pulsars as cosmic beacons, astronomers can explore extreme environments and test theories of dense matter and nuclear physics. The data gathered from pulsar observations helps us understand the evolution of stars and the structure of the universe, making pulsars indispensable in the field of contemporary astrophysics. Stellar black holes are another key component in the cosmic landscape. These regions of space have such strong gravitational forces that nothing, not even light, can escape their pull. Stellar black holes form from the remnants of massive stars. When a star with a core mass greater than approximately 3 solar masses exhausts its nuclear fuel, it can no longer resist its own gravitational force. The result is a catastrophic collapse, often followed by a supernova explosion. During the supernova phase, the outer layers of the star are expelled into space, enriching the surrounding environment with heavy elements. What remains behind is a black hole, an object so dense that its gravitational field warps spacetime itself. Black holes may seem mysterious, but they are vital to understanding the most extreme conditions of the universe, and their study can unlock secrets about gravity, time, and space itself. However, when a massive star reaches the end of its life, it collapses into an extremely dense state where gravity becomes the dominant force, overpowering all others. If the remaining mass of the star is sufficient, this collapse can continue until it reaches a point of infinite density, known as a singularity. This marks the creation of a stellar black hole, a region of space surrounded by an event horizon. The event horizon is a boundary beyond which nothing, no matter or light, can escape the black hole's immense gravitational pull. The formation of stellar black holes is a crucial event in the life cycle of massive stars. As these black holes form, they can have profound effects on their surroundings. One such effect is the release of energy in the form of powerful jets or X-rays when the black hole accretes material from a companion star or from surrounding gas. This energy output can become so intense that it outshines entire galaxies, making the black hole detectable even at great distances. The existence of stellar black holes offers astronomers valuable insights into the evolution of galaxies and the broader dynamics of the universe. By studying these enigmatic objects, scientists can unlock secrets about the processes that govern star formation and death, as well as the predictions made by general relativity. In this sense, stellar black holes act as natural laboratories, allowing us to test our understanding of the fundamental laws of physics and gain deeper insight into the complexities of the cosmos. Binary systems that include a black hole consist of two celestial objects, one of which is a black hole. In such systems, the black hole exerts a powerful gravitational influence on its companion star. This interaction can lead to fascinating phenomena that intrigue astronomers. The black hole may pull material from its companion star, particularly if that star extends beyond its Roche limit, the point which its own gravity is no longer strong enough to keep its material from being drawn into the black hole. This results in the formation of an accretion disk as material spirals inward toward the black hole. As the material accelerates, it heats up, emitting X-rays and other forms of radiation in the process. This radiation can become so bright that it provides astronomers with a way to indirectly observe black holes, which are otherwise invisible. The intense energy output from this accretion process makes these binary systems some of the most luminous objects in the universe, offering a glimpse into the nature of black holes and their interactions with surrounding matter. Moreover, these binary systems provide crucial clues about the life cycles of massive stars. When a massive star in such a system evolves and becomes a black hole, its companion star may also undergo significant changes in response. The interaction between the two can strip away layers from the companion star, altering its evolutionary path. This can lead to complex dynamics, such as mass transfer between the stars, which can influence their lifetimes and ultimate fates, offering us a deeper understanding of how stars evolve and end their lives. The study of binary black hole systems has uncovered some of the most fascinating predictions of general relativity, particularly in the realm of black hole interactions. When these colossal objects merge, they emit gravitational waves, ripples through the fabric of space-time, that have opened an entirely new window into astrophysical observation. Around the globe, observatories are now equipped to detect these faint signals, marking a revolutionary step in our understanding of the cosmos and the nature of gravity itself. Consequently, binary black hole systems have become critical not only for studying stellar evolution, but also for enhancing our grasp of the fundamental principles that govern the universe. The discovery of gravitational waves from these mergers has fundamentally changed the way we study cosmic events, providing us with data that was once only theorized. In a similar vein, we find the enigmatic Wolf-Rayet stars, massive, rare stellar objects in the late stages of their evolution. These stars, often 20 to 100 times the mass of our Sun, burn through their nuclear fuel at an extraordinary rate, producing intense, energetic outputs far beyond the typical stellar behavior. The Wolf-Rayet phase is marked by an active shedding of material through powerful stellar winds, which can be millions of times stronger than those of normal stars. What makes these stars so intriguing is the shedding of their outer hydrogen layers, revealing a hot, helium-rich core that can reach temperatures of up to 100,000 degrees Celsius. This extreme environment makes Wolf-Rayet stars crucial laboratories for understanding the life cycles of massive stars. Through nuclear fusion, these stars generate heavier elements like carbon, nitrogen, and oxygen. When they eventually explode in supernova, these elements are dispersed into the interstellar medium, enriching the cosmic landscape and playing a pivotal role in the formation of new stars and planets. Furthermore, the explosive deaths of Wolf-Rayet stars often result in the formation of black holes or even gamma-ray bursts, one of the most energetic phenomena in the universe. By studying these stellar giants, astronomers gain vital insights into the life cycle of massive stars and the processes that govern the universe's evolution. Similarly, planetary nebula, glowing shells of gas and dust ejected by aging stars, offer a breathtaking view of stellar death and rebirth. These nebulae form when low to intermediate mass stars, like our Sun, exhaust their hydrogen fuel. After expanding into red giants, these stars shed their outer layers, which are expelled into space and become the nebula. Planetary nebulae are not just beautiful, they serve as a rich source of information about the recycling of matter in the universe. The expelled gas contains essential elements like carbon, nitrogen, and oxygen, which were synthesized during the star's life. These elements are then spread into the interstellar medium, contributing to the formation of new stars, planets, and possibly even life itself. The study of planetary nebulae reveals crucial details about the late stages of stellar evolution, including how stars lose mass and how these processes shape the chemical evolution of galaxies. X-ray binaries, which are systems consisting of a compact object like a neutron star or black hole paired with a companion star, also contribute to our cosmic understanding. These systems are fascinating because of the intense X-ray emissions generated when the compact object pulls material from its companion. As this material spirals toward the compact object, it forms an accretion disk heating up to millions of degrees. This process converts gravitational potential energy into thermal energy, producing the X-rays we observe. Moreover, the presence of strong magnetic fields around neutron stars can accelerate charged particles, further amplifying the emission of X-rays through synchrotron radiation. This complex interaction between the two stars in an X-ray binary provides a powerful tool for studying extreme physics, particularly in the realms of gravity, magnetism, and matter under extreme conditions. In summary, these celestial phenomena, binary black holes, Wolf-Rayet stars, planetary nebulae, and X-ray binaries, are not merely beautiful or interesting. They are fundamental to our understanding of the universe's life cycle, offering insights into the forces, elements, and processes that shape the cosmos. The study of these stellar objects not only uncovers the mysteries of the universe, but also challenges our understanding of the laws of physics that govern all existence. Moreover, in some instances, explosive outbursts or jets can release high-energy radiation, further intensifying the X-ray emissions that define these celestial systems. X-ray binaries, which consist of a compact object like a neutron star or black hole and a companion star, are essential for unraveling various astrophysical phenomena. These systems provide a unique window into the formation and evolution of neutron stars and black holes. They also reveal crucial details about the dynamics of binary star systems and the effects of high-energy environments on ordinary matter. Through the study of X-ray binaries, astronomers can observe the life cycles of stars, understand the nature of gravitational interactions, and explore the intricate mechanics of high-energy astrophysics. As such, these systems hold immense significance in the quest to understand the universe itself. Astronomers detect and study gravitational waves emanating from merging black holes using highly sensitive instruments known as interferometers. The Laser Interferometer Gravitational Wave Observatory, or LIGO, is the most prominent of these detectors. These devices are designed to measure incredibly tiny distortions in space-time, distortions that are caused by cataclysmic events such as the merging of black holes. Gravitational waves create ripples in space-time, stretching and compressing space as they pass through. The process of detecting these waves involves splitting a laser beam into two perpendicular paths. The beams travel down long, evacuated tubes, reflect off mirrors, and then return to a central point. When a gravitational wave passes through, it affects the distances the beams travel, causing a shift in their interference pattern. This change can be minute, on the order of 1,000th the width of a proton. Yet LIGO and similar observatories are equipped with advanced technology and instrumentation to detect these faint signals. When LIGO detects a gravitational wave, a series of analysis steps follow to confirm the event's authenticity. The first task is to rule out noise from other sources, ensuring that the signal is indeed a gravitational wave and not an artifact of other phenomena. Once verified, astronomers can measure properties of the black hole merger, such as the masses of the black holes, the distance to the event, and the energy released during the collision. These data allow researchers to construct a detailed picture of the event, deepening our understanding of black hole formation and the dynamics of black hole mergers. Further observations often involve multi-messenger astronomy, where gravitational wave detections are combined with electromagnetic signals, such as gamma-ray bursts or X-rays, from the same event. This interdisciplinary approach enriches the data, offering new insights into the processes occurring during black hole mergers and to the very nature of gravity itself. As gravitational wave astronomy evolves, it promises to unveil even more about the universe, allowing us to explore cosmic phenomena previously beyond detection. One such phenomenon is the supernova, the explosive death of a star, which is classified into two primary types, Type 1 and Type 2. Type 1 supernovae occur in binary systems, where one of the stars is a white dwarf. When the white dwarf accretes enough matter from its companion, it reaches a critical mass and triggers a thermonuclear explosion, disrupting the star entirely. These supernovae are particularly significant in determining cosmic distances because of their consistent brightness, often serving as a standard candle in cosmology. On the other hand, Type 2 supernovae result from the core collapse of massive stars, typically those with more than 8 times the mass of the Sun. As these stars exhaust their nuclear fuel, their cores collapse under the force of gravity, leading to a rebound effect that results in a spectacular explosion. The outer layers of the star are ejected into space, enriching the surrounding region with heavy elements formed throughout the star's life. Both types of supernovae are crucial for galactic chemistry. When they explode, they release vast quantities of elements, including carbon, oxygen, and iron, key building blocks for the universe. These newly synthesized elements are vital for the evolution of future generations of stars, planets, and planets. For example, the oxygen and carbon produced in supernovae become integral components of molecular clouds, which eventually collapse to form new stars. The distribution of these elements also influences the dynamics and chemistry of galaxies. Supernovae can even trigger the formation of new stars by compressing nearby gas clouds, sparking increased star formation activity in their wake. Additionally, the shock waves generated by supernova explosions play a vital role in dispersing and mixing materials across the galaxy, creating a rich mosaic of chemical diversity. This process is essential for understanding the chemical evolution of galaxies over cosmic time, as it reveals how the universe transitions from the primordial hydrogen and helium produced in the Big Bang to the complex chemistry needed for life. Supernovae, therefore, are not simply destructive events. They are fundamental to the cycle of matter and to the very fabric of cosmic evolution. Astronomers study stellar remnants such as white dwarfs, neutron stars, and black holes to unravel the history of the Milky Way galaxy. These remnants serve as cosmic fossils, offering valuable insights into the processes that shape the galaxy over billions of years. By analyzing their properties, researchers can learn about the formation, evolution, and dramatic events that have taken place within our galactic home. One of the key ways in which stellar remnants contribute to our understanding of galactic history is through their ages and compositions. For instance, white dwarfs, which represent the final stages of low to intermediate mass stars, can be used to estimate the ages of star clusters. By determining how long it takes a white dwarf to cool after its formation, astronomers can estimate the age of the cluster. Different types of star clusters, such as open clusters and globular clusters, tell distinct stories about star formation and the dynamical evolution of our galaxy. Neutron stars and black holes also provide critical information about the life cycle of massive stars in the Milky Way. By studying the pulses of rapidly rotating neutron stars that emit beams of radiation, scientists can gain insights into the distribution of massive stars across the galaxy and observe phenomena like gravitational waves produced by merging black holes. Moreover, the remnants of supernova explosions enrich the interstellar medium with heavy elements, which contribute to the chemical evolution of the galaxy. These elements are crucial for understanding star formation rates and the conditions that foster the development of new stars and planets. In addition, stellar remnants reveal the history of interactions and mergers between different components of the Milky Way. For example, the presence of certain types of stars or specific chemical abundances can indicate past accretion events where the galaxy absorbed smaller satellite galaxies. This history of accretion and merger events has significant implications for the structure and dynamics of the Milky Way today. Through the careful study of stellar remnants, astronomers piece together the intricate tapestry of the Milky Way's history. These remnants do not merely signify the end of a star's life. They embody the evolutionary milestones of the galaxy, offering a clear lens through which the past can be explored and understood. The Great Attractor is a massive gravitational anomaly located in the direction of the constellations Centaurus and Hydra. At the heart of this region lies a concentration of mass that exerts a significant gravitational pull on galaxies, influencing their motion over vast cosmic distances. While the exact nature and composition of the Great Attractor are still subjects of research, it is generally understood to be an area that encompasses a large number of galaxy clusters, including the Norma cluster, along with considerable dark matter. The Great Attractor influences galactic motion primarily through its gravitational force. Galaxies that are relatively close to this region, including parts of the Milky Way and our neighboring galaxies, experience an acceleration toward it. This results in peculiar motion, often referred to as flows. These flows reveal a coherent path, indicating that multiple galaxies are not simply moving randomly, but are instead being drawn toward a common center of mass, an influence that can be traced over distances of several 100 million light-years. One intriguing aspect of the Great Attractor is its relationship with larger cosmic structures. It is part of a more extensive gravitational network beyond our local group of galaxies, which also includes the local supercluster. This hierarchical structure has far-reaching implications for the distribution of galaxies and clusters throughout the universe, showing how mass distribution influences cosmic evolution. The existence and influence of the Great Attractor challenge our understanding of the cosmos and the forces at play beyond what visible matter can account for. Much of the mass contributing to the Great Attractor is believed to be in the form of dark matter, an invisible substance that makes up a significant portion of the universe's total mass. By studying the dynamics of galactic movements in relation to this massive gravitational entity, astronomers gain vital insights into the behavior of galaxies, the mysterious nature of dark matter, and the overall large-scale structure of the universe. The unexpected rotation curves of galaxies are another fascinating aspect of astrophysics that challenges our understanding of gravity and mass distribution in the universe. Observations reveal that the outer regions of galaxies rotate much faster than would be predicted by the visible matter alone. According to the laws of gravity, we would expect the orbital speeds of stars and gas to decline with distance from the galactic center, much like how planets in the solar system move slower as they are further from the sun. However, what astronomers observe is a relatively flat rotation curve, indicating that stars at the outer edges of galaxies move at unexpectedly high speeds. The primary explanation for these unexpected rotation curves is the presence of dark matter. Dark matter is an unseen substance that does not emit, absorb, or reflect light, making it difficult to detect directly. Its gravitational influence, however, is evident in the movement of galaxies and provides a key clue in solving one of the greatest mysteries of the universe. However, its gravitational effects are clear when we observe the motions of stars and gas within galaxies. Evidence suggests that a significant amount of dark matter exists in halos that surround galaxies, extending far beyond the visible components. These dark matter halos add considerable mass, creating additional gravitational forces that cause stars in the outer regions of galaxies to move at higher speeds than would be expected based on visible matter alone, such as stars, gas, and dust. Another key factor in the dynamics of galaxy rotation curves is the history of galaxy formation. Over time, galaxies merge and interact with one another, leading to the redistribution of both visible and dark matter. These processes can alter the way mass is spread across a galaxy, influencing how stars are affected by gravitational interactions. The unexpected rotation curves observed in many galaxies raise profound questions about the nature of dark matter and the overall dynamics that govern these massive cosmic structures. The study of galactic rotation curves is pivotal for astronomers. It helps refine models of galaxy structure and formation while also providing insights into the composition of the universe. This research reveals a complex relationship between visible matter and the elusive dark matter that profoundly shapes the cosmos. In a related mystery, scientists are grappling with the missing baryon problem. This refers to a significant discrepancy between the amount of baryonic matter composed of protons, neutrons, and electrons that we expect to exist in the universe and the amount that has been detected through direct observation. Astronomical observations of galaxies, clusters, and the cosmic microwave background radiation suggest that only about half of the baryonic matter predicted is visible in stars, galaxies, and intergalactic gas. This leaves a substantial portion of baryonic matter seemingly unaccounted for, creating a puzzle for cosmologists. Several hypotheses have been proposed to explain this missing baryonic matter. One theory suggests that much of it may be hidden in the form of diffuse gas that is too faint to be detected with current technology. This gas could exist in vast cosmic voids with temperatures ranging from a few thousand to millions of degrees. When this gas is neither ionized nor concentrated enough, it becomes extraordinarily difficult to observe, creating the illusion that it is missing. Another possibility is that baryons are present as cold and warm gas clouds scattered throughout the intergalactic medium. These clouds could have formed during the early stages of cosmic structure formation and may reside between galaxies, contributing to the overall baryonic budget without being directly visible. Additionally, some theoretical models propose that baryonic matter could be hidden in non-luminous objects like rogue planets or brown dwarfs, objects that are not bright enough to be detected by our current instruments. Studies of galaxy formation and evolution also suggest that baryonic matter might cycle in and out of galaxies through processes such as supernova explosions and galactic winds. These events can eject gas and dust into the intergalactic medium, further complicating efforts to trace the baryons' original locations. Uncovering the missing baryons remains a major focus of research in astrophysics. As observational technologies improve and more advanced simulations of cosmic structure formation are developed, astronomers are hopeful that the hidden baryonic matter will be detected. Understanding this missing component is essential for developing a more complete picture of the universe's composition and refining our models of cosmic evolution, offering deeper insights into the workings of the cosmos. Another profound mystery is dark energy, a mysterious form of energy that permeates all of space. It is believed to be responsible for the accelerated expansion of the universe and accounts for approximately 70% of the total energy density of the cosmos. Yet despite its prevalence, the exact nature of dark energy remains one of the most puzzling unresolved problems in modern cosmology. Unlike matter, which clumps together under the influence of gravity, dark energy appears to exert a repulsive force, driving galaxies apart and causing the expansion of the universe to accelerate over time. The effects of dark energy were first inferred from observations of distant supernovae in the late 20th century. Researchers noticed that these supernovae were dimmer than expected, suggesting that they were farther away than previously thought. This observation implied that the expansion of the universe was not only continuing, but accelerating, contradicting the earlier belief that gravitational forces would gradually slow the expansion over time. This groundbreaking realization led to the widespread acceptance of dark energy as a driving force behind the cosmos's accelerated expansion. Cosmologists often model dark energy using a concept called the cosmological constant, which was introduced in Einstein's theory of general relativity. In this framework, dark energy remains constant over time. It does not evolve as the universe expands, and its energy density stays the same. This idea continues to shape the study of dark energy, offering a potential explanation for the mysterious force that governs the fate of the universe. However, other theories propose that dark energy could belong to a dynamic field with properties that evolve over time, a concept known as quintessence. Despite the variety of theories, the fundamental characteristics of dark energy remain elusive. The influence of dark energy on galactic expansion carries profound implications for the fate of the universe. Under its effect, galaxies are expected to continue moving away from each other at an accelerating rate. This means that over billions of years, distant galaxies will recede beyond the observable universe, leading to a future where the night sky will be devoid of most of the galaxies we see today. Understanding dark energy is essential not only for clarifying the current state of the universe, but also for predicting its ultimate fate. As research continues, scientists aim to unveil the true nature of dark energy, which could reshape our understanding of the cosmos and the fundamental forces at play. The Milky Way is surrounded by a number of satellite galaxies, but many astronomers have observed an apparent lack of smaller ones, which has posed a puzzling question. Current observations reveal over 50 smaller satellite galaxies, but models of galaxy formation suggest there should be many more. This discrepancy has led scientists to explore various explanations. One compelling theory revolves around the gravitational influence of the Milky Way itself. The galaxy's larger gravitational pull may strip away gas and stars from smaller galaxies as they approach. This process, known as tidal stripping, can cause these smaller systems to lose their material and eventually become difficult to detect. It is possible that these satellites existed in the past, but were disrupted or diminished over time. Another factor to consider is the feedback from star formation in smaller galaxies. The energy and radiation from young stars can blow away gas, preventing the formation of new stars and potentially causing these galaxies to fade away. This phenomenon might inhibit the formation of many smaller satellites in the first place, especially in environments influenced by larger galaxies like the Milky Way. Astrobiologists have also speculated that the formation of small galaxies may have been affected by cosmic reionization. After the Big Bang, the universe underwent a period of reionization that heated up and ionized the gas. This event could have limited the formation of smaller structures during a critical phase of the universe's development, explaining the lower observable numbers of satellite galaxies surrounding large galaxies like ours. As researchers continue to investigate these dynamics, new insights may emerge, shedding light on the intriguing story of our galaxy's satellite companions. High-velocity clouds, HVCs, are another fascinating feature in the galactic halo, and their origins have sparked significant interest among astronomers. These clouds, composed of hydrogen gas, move at speeds significantly different from the more orderly rotation of the Milky Way. Their presence suggests dynamic processes are occurring within our galaxy's environment. Several hypotheses have been proposed to explain their origin. One prominent theory is that HVCs are remnants of past interactions with nearby galaxies. When smaller galaxies or intergalactic gas clouds merge or collide with the Milky Way, they can create these high-velocity clouds. The interactions impart substantial kinetic energy to the gas, causing it to accelerate and appear as HVCs in the vast halo surrounding our galaxy. Another possibility is that these clouds could be primordial, formed shortly after the Big Bang. They might represent regions of gas that failed to coalesce into stars or larger structures, remaining as isolated, high-velocity entities. These primordial clouds could contain materials essential for future star formation, influencing the evolution of the Milky Way as they interact with its gravitational field. Some researchers also propose that high-velocity clouds may originate from processes occurring deep within the Milky Way itself. Outflows generated by star formation or the activity of supermassive black holes at the galactic center might propel gas into the halo, creating HVCs. This phenomenon illustrates the ongoing interactions and exchanges of matter that shape the content and structure of our galaxy. As studies progress, we continue to uncover the intricate layers of forces that give rise to the mysterious and captivating high-velocity clouds in our universe. Ultra-diffuse galaxies stand out as one of the most striking and puzzling types of astronomical objects, defying conventional understanding of galaxy formation. These galaxies possess an extraordinarily low surface brightness and a vast physical size when compared to their stellar mass. Unlike traditional galaxies, which feature a dense concentration of stars at their core, ultra-diffuse galaxies display a more spread out, diffuse distribution of stars, making them incredibly difficult to detect. The existence of these galaxies has forced scientists to rethink how galaxies can evolve in the cosmos. One widely discussed theory suggests that ultra-diffuse galaxies may originate from larger galaxy clusters. During their formation, they could have undergone violent interactions with nearby galaxies, leading to the stripping away of gas and stars. The tidal forces exerted during these close encounters could stretch and distort the galaxy, leaving behind a galaxy with a much lower stellar density. This scenario implies that ultra-diffuse galaxies might actually be remnants of much larger galaxies that have been severely affected by gravitational forces. Another hypothesis offers a completely different perspective. Ultra-diffuse galaxies could represent a previously unconsidered evolutionary pathway for galaxy formation. In this view, they might arise from the rapid collapse of gas clouds in the early universe, without the intense stellar feedback often triggered by star formation. This accelerated collapse could lead to the creation of a galaxy rich in dark matter but relatively sparse in stars, explaining the low surface brightness that defines these enigmatic objects. The role of dark matter in ultra-diffuse galaxies cannot be underestimated. These galaxies may contain substantial amounts of dark matter, which plays a crucial role in maintaining their structure. Despite their relatively sparse stellar populations, the presence of dark matter could help stabilize the galaxy, allowing it to remain intact and cohesive. The dynamics of dark matter in these galaxies might hold the key to understanding how they can remain stable over time, despite the apparent lack of stars. As we continue to study these fascinating objects, we gain deeper insights into the various paths through which galaxies can evolve over the vast stretch of cosmic time. In a different corner of the universe, another captivating mystery unfolds: fast radio bursts, or FRBs. These powerful, brief bursts of radio waves originating from deep space have captured the imagination of astronomers and researchers around the world. Lasting only a few milliseconds, these bursts appear suddenly, releasing vast amounts of energy in an instant. Their brief but intense emissions present a significant puzzle, with their origin remaining a source of intense speculation. While the exact cause of FRBs is still unknown, several theories have been proposed to explain their origins. One popular hypothesis suggests that they could be the result of rapidly rotating neutron stars, also known as pulsars. Pulsars, with their powerful magnetic fields and rapid rotation, can generate bursts of electromagnetic radiation. Some researchers believe that certain neutron stars may possess properties that enable them to emit these exceptionally bright radio signals, particularly when interacting with nearby material. Another intriguing possibility links FRBs to magnetars, neutron stars with extraordinarily strong magnetic fields. When magnetars undergo dramatic events such as starquakes or magnetic field rearrangements, they may emit bursts of high-energy radiation. The idea of magnetar-related FRBs has gained considerable traction, particularly since some of these bursts have been observed to repeat, suggesting a more active and explosive origin. This repetitive behavior points to a source that is not only powerful but also capable of recurring outbursts, adding another layer of complexity to the mystery of FRBs. Speculation continues to mount that the phenomenon might be tied to events on a cosmic scale, such as collisions between compact objects or even interactions involving black holes. The sheer number of possible explanations highlights the vast complexity of the physical processes that could lead to the creation of fast radio bursts. As more observations are made and advanced technologies come online, researchers are hopeful they will unravel this cosmic riddle, shedding light on the origins of these brief yet powerful signals from the universe. The thick disk of a galaxy stands out as one of its most intriguing components, situated above and below the central plane of the thin disk, where most of the galaxy's stars are concentrated. This thick disk is unique in both structure and composition. It is characterized by a greater height, a higher density of older stars, and a distinct population of stars with different ages and chemical compositions compared to those found in the thinner disk. Understanding the formation and characteristics of the thick disk is crucial for piecing together the history of not only our own galaxy but others as well. One prominent explanation for the origin of the thick disk revolves around the processes that shape a galaxy's formation and evolution. In the early stages of a galaxy's life, interactions with other galaxies, such as mergers and the accretion of gas, can disperse stars into a thicker structure. These gravitational interactions can perturb stars, imparting enough energy for them to move away from the flat plane of the thin disk, ultimately giving rise to what we observe as the thick disk. Additionally, internal processes within the Milky Way may contribute to the formation of the thick disk. As stars form and evolve, some may explode as supernovae, enriching the surrounding environment with heavier elements. The energy released in these explosive events can stir up stars in the thin disk, contributing further to the creation of the thick disk. In many cases, the thick disk is populated by older stars that have remained relatively unchanged since their formation. This suggests that the thick disk may harbor remnants from the early universe, offering valuable clues to the conditions that existed at that time. The study of the thick disk is a dynamic area of research that helps astronomers unravel the complex assembly of the Milky Way, offering new insights into the evolution of galaxies across the universe. Ultra-high energy cosmic rays represent another fascinating aspect of the cosmic landscape. These charged particles possess energies that exceed 1 billion electron volts. The origin of these mysterious particles is believed to lie in powerful astrophysical phenomena. Understanding their sources not only deepens our knowledge of cosmic rays, but also offers a window into the extreme conditions of the universe. One leading hypothesis is that supernova remnants contribute significantly to the creation of ultra-high energy cosmic rays. When massive stars run out of nuclear fuel, they explode in supernova events, releasing an enormous amount of energy. The shockwaves produced by these explosions accelerate particles to extraordinary speeds, generating cosmic rays. As these remnants evolve, they provide the ideal environment for the acceleration processes that lead to the creation of ultra-high energy particles. Active galactic nuclei, which house supermassive black holes at the centers of galaxies, including our own Milky Way, are another intriguing potential source of these high-energy cosmic rays. These black holes can power jets of high-energy particles that travel vast distances through space. The extreme conditions surrounding these jets might be responsible for generating ultra-high energy cosmic rays, as particles are accelerated to incredibly high speeds within intense gravitational and magnetic fields. Gamma-ray bursts, some of the most energetic events in the universe, are also considered strong candidates. Occurring during the collapse of massive stars or the collision of neutron stars, these bursts release immense amounts of energy in brief periods, and they too can accelerate particles to incredibly high energies. While these potential sources offer valuable insights into our understanding of cosmic rays, the precise mechanisms behind the creation of ultra-high energy cosmic rays remain an area of active research. Ongoing observations and advancements in detection technology will help to clarify their origins, enhancing our understanding of the dynamic processes taking place not just in our galaxy, but throughout the universe. The discovery of exoplanets, planets that exist outside our solar system, marked a pivotal moment in the field of astronomy and revolutionized our understanding of planetary systems. Before the first confirmed detection of an exoplanet in the mid-1990s, our knowledge of planets was limited to the 8 that orbit our sun. The realization that planets could exist around other stars opened an entirely new frontier in astrophysics, with profound implications for how we understand the formation and evolution of planetary systems. The methods used to detect exoplanets, such as the transit method and radial velocity technique, have revealed a breathtaking diversity of planetary systems within our galaxy. Many of these exoplanets differ drastically from the familiar worlds of our solar system. Astronomers have discovered hot Jupiters, massive gas giants that orbit extremely close to their host stars, as well as Earth-sized rocky planets in the habitable zone, where conditions may be suitable for life. This incredible diversity challenges existing models of planetary formation, suggesting that the processes leading to the creation of planets are far more complex and varied than previously believed. The discovery of thousands of exoplanets, each one a potential world in its own right, suggests that our solar system is one of many possible configurations in the vast universe. This realization has spurred the development of new theories on how planetary systems can form in a variety of environments. For example, the presence of multiple planets in compact orbits around a single star could point to entirely different mechanisms of planetary formation and migration compared to the arrangement we observe in our own solar system. This exploration of distant worlds has also reignited age-old questions about the possibility of life beyond Earth. By analyzing the atmospheres of certain exoplanets, astronomers have the potential to detect biosignatures or conditions that could support life. The search for extraterrestrial life reaches beyond the realms of science, influencing our views in philosophy, biology, and even shaping our understanding of humanity's place within the cosmic landscape. As scientists continue to uncover more exoplanets, each discovery adds to the grand narrative of cosmic exploration, expanding our understanding of planetary systems and our place in the universe. But the quest for knowledge does not end there. The detection of gravitational waves has opened a whole new chapter in our understanding of the cosmos, allowing astrophysicists to observe some of the most violent and energetic phenomena in the universe in a way that was once unthinkable. Gravitational waves were first predicted over a century ago by Albert Einstein as part of his theory of general relativity. These ripples in space-time, caused by the violent collision of objects like black holes or neutron stars, provide a unique opportunity to study cosmic events from a completely new perspective. The first detection of gravitational waves in 2015 by the LIGO Observatory was a landmark moment in astronomy. It confirmed the existence of these elusive waves and offered direct evidence of black hole mergers, giving us insight into their properties, such as their mass and spin. Before this breakthrough, black holes could only be studied through indirect evidence. Now, gravitational waves allow us to observe these enigmatic objects firsthand. But the implications of gravitational wave detections extend far beyond black holes. In 2017, astronomers observed the merger of two neutron stars, an event that also produced gravitational waves. This was groundbreaking, as it marked the first ever multi-messenger astronomy event, a simultaneous observation of both gravitational waves and electromagnetic signals. The ability to study both types of signals during such a catastrophic event has opened up new frontiers in astrophysics. It has provided unprecedented insights into the creation of heavy elements like gold and platinum, which are believed to form in the aftermath of neutron star collisions. By unlocking the secrets of these cosmic collisions, scientists are reshaping our understanding of the universe's most violent processes and the origins of the elements that make up our world. Moreover, the study of gravitational waves holds the potential to probe the very fabric of space-time itself. This groundbreaking field opens up pathways to explore fundamental questions about the universe, such as the nature of gravity, the behavior of matter under extreme conditions, and even the possibility of uncovering secrets from the universe's earliest moments shortly after the Big Bang. As gravitational wave detection technology continues to improve, it promises to deepen our understanding of cosmic phenomena and unravel some of the universe's most profound mysteries. At the same time, the mapping of the cosmic microwave background radiation, CMB, has revolutionized our understanding of the universe, refining cosmological models in ways once thought impossible. The CMB represents the afterglow of the Big Bang, remnant radiation that fills the cosmos and provides a snapshot of the universe when it was just about 380,000 years old. By studying this ancient light, astronomers can gain insights into the conditions that shaped the early universe. Detailed observations from missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have provided incredibly precise maps of the CMB. These maps reveal tiny fluctuations in temperature across the sky, which correspond to density variations in the early universe. These anisotropies act as a record of the primordial density fluctuations that eventually gave rise to the galaxies and large-scale structures we see today. By analyzing these patterns, scientists can infer critical parameters like the universe's rate of expansion, its composition, and its overall geometry. The refined measurements of the CMB have corroborated and enhanced the standard cosmological model known as lambda cold dark matter, LCDM. According to this model, the universe is composed of roughly 70% dark energy, 25% dark matter, and 5% ordinary matter. This framework has provided a comprehensive explanation for a wide range of astronomical observations, making it one of the most successful models in understanding large-scale cosmic evolution. Yet, the mapping of the CMB has also sparked new questions and avenues of research. Discrepancies between measurements of the universe's expansion rate, known as the Hubble constant, derived from CMB data and those obtained from local observations, have sparked debates and investigations into potential new physics beyond the standard model. As researchers continue to analyze CMB data, they not only refine our current understanding, but also pave the way for breakthroughs that could reshape cosmological theories and reveal deeper truths about the universe. Meanwhile, multi-messenger astronomy is transforming our approach to studying the cosmos. This innovative field combines information from different astrophysical signals, ranging from electromagnetic radiation to gravitational waves, neutrinos, and cosmic rays. Over the past few years, it has led to significant discoveries and expanded our understanding of the universe's most extreme phenomena. One of the most notable milestones in multi-messenger astronomy occurred in 2017 with the merger of neutron stars. This event was extraordinary, not only because it was detected through gravitational waves, but also because it was simultaneously observed across multiple electromagnetic wavelengths, from gamma rays to optical light. This was the first time astronomers had been able to correlate gravitational waves with electromagnetic observations, revealing vital information about neutron star collisions and the processes involved in heavy element production. From this observation, researchers learned that such events are responsible for creating elements like gold and platinum, forging a powerful link between cosmology and nuclear synthesis. Additionally, the simultaneous detection of multiple types of messengers has allowed scientists to confirm or challenge existing theories about the origins of cosmic rays. These high-energy particles, composed of charged particles from various sources, have long been associated with phenomena such as gamma-ray bursts and supernovae. Multi-messenger studies have now provided critical evidence for understanding how these ultra-high-energy particles are accelerated and where they originate in the universe. Moreover, the emergence of new observatories dedicated to detecting a variety of astrophysical signals has drastically expanded the opportunities for multi-messenger observations. These advancements are revealing fresh perspectives on some of the universe's most extreme phenomena, such as active galactic nuclei and supernovas. By capturing high-energy neutrinos, subatomic particles generated in the heart of these violent environments, scientists are uncovering new layers of understanding about the fundamental processes that govern the evolution of the cosmos. These observations are not only shining a light on the highest energies ever recorded, but are also unlocking the interactions between matter and energy that occur in these extreme conditions. The growth of multi-messenger astronomy underscores the collaborative nature of modern astrophysics, where diverse scientific disciplines converge to solve the mysteries surrounding violent cosmic events. As researchers continue to refine detection methods and enhance data sharing capabilities, the future of this field promises even greater revelations. The insights gained will push the boundaries of our understanding of the underlying mechanics of the universe itself. In addition, deep field observations have revolutionized our grasp of galaxy formation and evolution. By focusing on small, seemingly inconspicuous patches of the sky for extended periods, astronomers have been able to capture the faint light of distant galaxies that would otherwise remain undetected. The Hubble Space Telescope's deep field images, in particular, have uncovered thousands of galaxies, each one telling a unique story about the cosmos's history. These observations allow us to study the universe across different epochs by examining galaxies at varying distances, distances that correspond to different times in the universe's timeline. Tracking these galaxies across billions of years has led to the discovery that much of galaxy formation occurred when the universe was relatively young. This provides invaluable insights into the processes driving star formation and the development of galactic structures. In doing so, scientists have uncovered a range of galaxies that were previously unaccounted for in theoretical models, challenging our understanding of galaxy evolution. Notably, many of these newly discovered galaxies are young and irregular, shedding light on previously unknown pathways of formation. This complexity forces us to reconsider the traditional view of galaxy progression, which was once thought to follow a straightforward path from smaller, irregular shapes to larger, more organized spirals and ellipticals. Instead, what we are finding suggests that galaxy formation is far more intricate. It is influenced by a multitude of factors, including mergers, interactions, and environmental conditions, making it increasingly difficult to model the evolution of galaxies over time. Moreover, deep field imaging has offered new insights into the role of dark matter in galaxy formation. The distribution of galaxies observed in these images strongly supports the theory that dark matter forms the invisible framework upon which galaxies are built. Understanding the relationship between visible matter, such as stars and gas, and dark matter is crucial for developing more accurate models that explain the observed structure of the universe. As technology advances and more sophisticated observatories come online, deep field studies will continue to play a pivotal role in unveiling the complexities of galaxy formation. These observations help astronomers piece together the intricate puzzle of how galaxies like our own Milky Way came to be, providing a dynamic view of the universe's history. Recently, observations of galaxies have significantly advanced our understanding of dark matter, an enigmatic substance that makes up approximately 26% of the universe's total mass energy content. Although dark matter does not emit, absorb, or reflect light, its gravitational effects are detectable in the motion of galaxies, galaxy clusters, and even in the cosmic web that connects them. These observations have provided critical insights into the distribution, nature, and dynamics of dark matter across the universe. One of the key breakthroughs in dark matter research has come from studying the rotation curves of galaxies. By measuring the speeds of stars and gas in the outer regions of galaxies, scientists discovered that these rotational speeds remain unexpectedly high, even at large distances from the galactic center. According to the laws of gravity, stars further from the center should rotate more slowly due to the diminishing gravitational pull of visible matter. However, the observed high speeds point to the presence of an unseen mass, dark matter, that influences the gravitational potential of galaxies. This discovery led to the development of dark matter halo models, which describe how dark matter is distributed around and within galaxies, shaping their structure and behavior. Observations of galaxy clusters have been instrumental in unraveling the behavior of dark matter on larger scales. By measuring the mass of clusters through a phenomenon known as gravitational lensing, where light from distant objects is distorted by the cluster's gravitational field, astronomers have mapped the distribution of dark matter. These maps reveal a striking pattern. Dark matter often forms a halo around visible matter, acting as an invisible framework for galaxies within clusters. The study of these mass distributions has solidified the idea that dark matter is crucial for holding clusters together, profoundly influencing their evolution over cosmic time. Additionally, the discovery of the cosmic web, a vast network of interconnected filaments formed by dark matter, has expanded our understanding of the universe's structure. Observations of galaxy redshifts have shown that galaxies are not scattered randomly across the cosmos, but follow intricate patterns dictated by dark matter's gravitational influence. This work has reinforced the notion that dark matter plays a pivotal role in shaping the large-scale structure of the universe, determining how galaxies are arranged and how they interact over billions of years. As observational techniques improve and new surveys are conducted, our understanding of dark matter continues to evolve. Future discoveries are poised to deepen our insights into this elusive substance, shedding light on fundamental questions about gravity, the formation of cosmic structures, and whether dark matter consists of known particles or exotic new ones. Space-based observatories have revolutionized our view of the Milky Way, providing astronomers with unparalleled access to data that enhance our understanding of our galaxy's structure, dynamics, and composition. Unlike ground-based telescopes, which are affected by Earth's atmosphere, space-based instruments capture clearer, more detailed observations across a wide range of wavelengths: visible, infrared, and radio light. One of the most significant advancements has come from instruments like the Hubble Space Telescope, which has offered breathtaking images and insights into individual stars, star clusters, and the formation of new stars within our galaxy. Hubble's ability to peer into stellar nurseries has provided new understanding of the processes governing star formation and how these processes vary across different regions of the Milky Way. Alongside infrared telescopes like the Spitzer Space Telescope, capable of penetrating dust clouds that obscure visible light, astronomers now have a clearer view of the galaxy's inner workings. Moreover, missions like the European Space Agency's Gaia Observatory have transformed our knowledge of the Milky Way by creating a detailed three-dimensional map of its stars. Gaia's astrometric measurements have allowed scientists to pinpoint the positions, distances, and motions of over 1 billion stars, revealing intricate details of the galaxy's structure and dynamics. This mapping has helped identify the distribution of stars, stellar clusters, and the overall shape of the Milky Way, enhancing our understanding of its spiral arms and the varying populations of stars, ranging from ancient stars to younger ones, and those with unique chemical compositions. In addition to mapping stars, space observatories have deepened our comprehension of the Milky Way's dark matter content. Observations of stellar motions within the galaxy, combined with space-based measurements, have provided strong evidence of a dark matter halo surrounding the Milky Way. These findings offer valuable insights into how the galaxy's gravitational pull influences its stars and gas, shedding light on the role dark matter plays in the galaxy's formation and evolution. Ultimately, space-based observatories have become indispensable tools in astronomical research, offering a more detailed and nuanced view of the Milky Way. As technology continues to evolve, future missions hold the promise of even greater discoveries, guiding us closer to understanding our galaxy's history, structure, and its place within the broader universe. High redshift galaxy observations have also provided invaluable insights into the early universe, allowing astronomers to explore regions that existed when the universe was just a fraction of its current age. These distant galaxies, formed between 2 to 10 billion years after the Big Bang, correspond to epochs when the universe was more dynamic and rapidly evolving. Studies of these distant galaxies have uncovered critical information about the formation, evolution, and properties of early cosmic structures. One major discovery is that galaxies in the early universe appear more irregular and chaotic compared to their more mature counterparts today. Many high redshift galaxies show signs of intense star formation and are often smaller and less structured than present-day galaxies like our Milky Way. This suggests that the processes driving galaxy formation in the early universe were very different, leading to rapid star and gas accumulation. The heightened star formation rates indicate that the early cosmos was an active environment, with galaxies frequently interacting and merging, events that would eventually lead to the larger, more organized structures we see today. Moreover, high redshift observations have opened a window into the early chemical evolution of the universe. By studying the light emitted from distant galaxies, astronomers can detect the signature of various elements. These observations reveal that the early universe was dominated by hydrogen and helium, with heavier elements gradually forming through stellar processes. The rate at which these metallic elements were created provides crucial insights into the life cycle of stars and how the abundance of heavier elements evolved over time. At the same time, the cosmic history of dark matter has also been illuminated. High redshift galaxies offer researchers a unique opportunity to study the formation and evolution of dark matter halos alongside visible matter. The intricate relationship between dark matter and baryonic matter in the early universe has proven essential for refining cosmological models. This understanding sheds light on how gravity influenced the structure formation that would later become the foundation of the modern universe. With more advanced tools like the James Webb Space Telescope, astronomers are poised to deepen their understanding of the processes that shaped the universe in its infancy. These ongoing observations hold the promise of revealing more about the origins and evolution of galaxies, ultimately contributing to the quest to understand our cosmic history and the fundamental forces that govern the universe. In addition to these monumental discoveries, the detection of interstellar objects, such as Oumuamua, has profoundly shifted our perspective on both our solar system and the broader dynamics of our galaxy. When Oumuamua passed through our solar system in 2017, it became the first known object not gravitationally bound to the Sun, revealing that it had originated from another star system. This groundbreaking discovery sparked a new chapter in astronomy, showing that our solar neighborhood is not an isolated environment, but a dynamic one, filled with potential visitors from distant star systems. One of the most significant implications of Oumuamua's passage is the realization that interstellar objects may be more common than previously thought. This has prompted astronomers to reconsider our understanding of material distribution within the galaxy. Until now, most of our knowledge about celestial objects came from those within our solar system. The discovery that interstellar objects, such as fragments of other star systems and potentially even habitable planets, can traverse interstellar space challenges long-held assumptions. The peculiar characteristics of Oumuamua, its cigar-like shape and lack of detectable cometary activity, have raised many questions about its nature and origin. Unlike typical comets or asteroids, Oumuamua's unusual behavior has led to various theories about its composition, including the possibility that it is a fragment of a larger body or an object shaped by extreme forces in a distant solar system. These discussions have prompted broader investigations into the diverse range of interstellar objects that might exist and the physical processes that shape them. Moreover, the study of interstellar objects holds significant implications for astrobiology. By understanding the materials and conditions present in other star systems, scientists can learn more about the potential for life beyond our own. Some researchers even speculate that interstellar objects could carry organic compounds or other essential ingredients for life, possibly delivering them to planets during their formation or evolution. This exciting prospect encourages scientists to explore how life could emerge in a variety of environments, further fueling the ongoing search for extraterrestrial life. The excitement sparked by Oumuamua has led to plans for more active searches and studies of additional interstellar visitors. Future telescopes and missions will likely enhance our ability to detect and analyze these intriguing objects. These advancements will expand our understanding of the solar system and the myriad cosmic interactions that shape the universe around us. Meanwhile, recent studies of the stellar populations in the galactic bulge have provided profound insights into the formation and evolution of the Milky Way. The galactic bulge, a densely populated region at the center of our galaxy, contains a rich variety of stars, many of which are old and metal-rich. These stellar populations hold essential clues about the history and dynamics of the Milky Way. A key discovery has been the diversity of stellar populations within the bulge itself. Observations have shown that the bulge is not made up solely of old stars, as was once assumed. Instead, it includes a mixture of stars of different ages and metallicities. This diversity suggests that the bulge formed over an extended period, with different episodes of star formation contributing to its current structure. The presence of younger stars alongside older populations implies that star formation was more active in the bulge than previously believed, likely influenced by interactions with surrounding gas and the dynamic forces of nearby galactic structures. In recent years, advanced spectroscopic techniques have opened a window into the heart of our galaxy. These studies have revealed the importance of understanding the chemical composition of stars in the galactic bulge. By examining the abundance of elements within these stars, astronomers have been able to trace the intricate process of chemical enrichment across generations. The variety of metallicities observed tells a compelling story. Some stars formed from gas enriched by the very stars that preceded them. This process provides a timeline for the evolution of the bulge, offering a glimpse into the early dynamics that shaped this region. This evolving understanding aligns with models suggesting the Milky Way's early growth was driven by both the collapse of gas clouds and the subsequent accretion of material from its surroundings. Moreover, kinematic studies of the stars in the bulge have revealed profound insights into the structure and motion of this central region. Within the bulge, stars exhibit a complex dance, moving through different components, including a classical spheroid and a more dynamic bar structure. This complexity suggests that the bulge has undergone significant gravitational interactions, with stars migrating and reshaping the region over time. These movements are crucial in piecing together the Milky Way's evolutionary history and understanding the pivotal role the bulge played in shaping the galaxy as we know it. As astronomers continue to deploy cutting-edge telescopes and techniques to study the stars in the galactic bulge, our understanding of this region will only deepen. The ongoing exploration of the bulge's origins, chemical composition, and stellar dynamics sets the stage for a more comprehensive view of the Milky Way's past and the processes that have driven galaxy evolution over cosmic time. Enter the James Webb Space Telescope. Launched in December 2021, this technological marvel represents a leap forward in our ability to explore the Milky Way and its myriad structures. Equipped with state-of-the-art instruments, Webb is poised to provide unprecedented insights into areas that have long challenged astronomers. One of its key advantages is its ability to observe the galaxy in the infrared spectrum. Many regions of the Milky Way, especially areas of active star formation, are hidden by thick layers of dust which block visible light. Webb's infrared capabilities will pierce through this veil, unveiling the hidden details of stellar nurseries where new stars and planetary systems are taking shape. This breakthrough will enhance our understanding of the mechanisms behind star formation and the conditions necessary for new stars to emerge. But Webb's potential goes far beyond just studying stellar birth. It will also offer detailed surveys of the Milky Way's structure and dynamics, from the bulge to the disk and halo. By observing the distribution of stars, gas, and even dark matter, astronomers will gain new insights into the galaxy's formation history and the complex processes that have shaped its structure over billions of years. Furthermore, Webb will play a crucial role in the hunt for exoplanets. Its advanced spectrographs will allow astronomers to study the atmospheres of planets orbiting distant stars, particularly those in the habitable zones where life might be possible. By analyzing the light passing through these atmospheres during transits, Webb will enable scientists to search for biosignatures, bringing us one step closer to understanding the potential for life beyond Earth. As the James Webb Space Telescope unlocks new secrets of the Milky Way, it will not only deepen our understanding of our own galaxy, but also illuminate the vast cosmos beyond. Moreover, the ability to conduct deep field observations with the James Webb Space Telescope will allow astronomers to identify distant faint objects, including those that may represent the early stages of galaxy formation. By observing these remote galaxies and tracing their formation in relation to our own Milky Way, scientists will gain invaluable insights into the evolution of galaxies over cosmic time. This powerful tool promises to transform our study of the Milky Way, providing clearer, more detailed views of its structure, evolution, and the complex processes that unfold within it. As Webb begins collecting data, it will open new avenues of research, deepening our understanding of our galaxy's place in the vast universe. At the same time, adaptive optics represents a significant leap forward in ground-based astronomical observations, offering a solution to one of the primary challenges faced by traditional telescopes: Earth's turbulent atmosphere. Atmospheric distortion has long blurred the images of celestial objects, limiting the clarity and precision of our observations. But with recent advancements in adaptive optics technology, astronomers can now enhance their ability to study the Milky Way and other galaxies from the ground with unprecedented sharpness. One of the key breakthroughs in this field is the development of more sophisticated wavefront sensors and correcting algorithms. These systems can swiftly measure the distortion in light caused by atmospheric turbulence, then adjust the telescope's optics in real time. By harnessing advanced algorithms and artificial intelligence, astronomers can optimize these corrections, enabling telescopes to capture sharper and more detailed images of stars, nebulae, and other features within our galaxy. With improved correction capabilities, these systems not only enhance spatial resolution, but also boost contrast, allowing astronomers to resolve finer details than ever before. Another notable advancement is the integration of multiple adaptive optics systems onto a single telescope, a technique known as multi-conjugate adaptive optics. By using several deformable mirrors at different points in the optical path, this configuration enables corrections across a wider field of view. As a result, astronomers can study larger regions of the Milky Way simultaneously, all while maintaining the high image quality offered by adaptive optics. This capability is particularly useful for mapping large-scale features like star clusters and extended nebulae. The advent of high-order adaptive optics is also a game-changer. Traditional systems typically correct for a limited number of distortion modes, but high-order systems can address a broader range of distortions, leading to even sharper images, especially under turbulent conditions. This is invaluable when observing smaller-scale astronomical phenomena, such as the dynamics of stars in the central bulge of the Milky Way. Furthermore, the development of laser guide stars has dramatically expanded the utility of adaptive optics. By projecting a laser beam into the atmosphere, astronomers can create an artificial star that mimics the behavior of a natural one. This allows for more accurate wavefront corrections in areas where natural guide stars are absent, improving observations in regions of the sky that would otherwise be difficult to study. Laser guide stars are particularly valuable for studying densely populated areas of the Milky Way, like star clusters in the galactic core. As these advancements in adaptive optics continue to evolve, they hold the potential to revolutionize our ability to observe the Milky Way and beyond. Enhanced image quality will allow astronomers to investigate the dynamics and composition of stars, gas, and dust, leading to groundbreaking discoveries about the structure and history of our galaxy. Gravitational lensing is another powerful phenomenon that promises to unlock new insights into distant parts of the galaxy. This occurs when a massive object, such as a galaxy or galaxy cluster, exerts a strong gravitational pull, bending the light from more distant objects behind it. This bending of light amplifies and distorts the images of background objects, providing astronomers with valuable information about both the foreground lensing object and the distant sources of light. One of the most exciting applications of gravitational lensing in the study of distant galaxies is the magnification of faint objects. When a massive galaxy or cluster acts as a lens, it can enhance the brightness and resolution of more distant galaxies that would otherwise be too faint to detect. This amplification allows astronomers to observe objects located much further back in the universe, providing insights into their structure, star formation rates, and chemical composition. By analyzing the light from these lens galaxies, researchers can reconstruct information about their environment and evolutionary history. Gravitational lensing also serves as a powerful tool for mapping the distribution of dark matter. The amount of distortion in the light from lensed galaxies is directly related to the mass of the lensing object. By studying these lensing effects, astronomers can create mass maps of the lensing galaxy or cluster, revealing where dark matter is concentrated. This information is crucial for refining our understanding of the role that dark matter plays in galaxy formation and evolution, offering new perspectives on the cosmos on both large and small scales. Gravitational lensing plays a crucial role in advancing our understanding of the cosmos. By bending light around massive objects, it offers a unique opportunity to probe the universe's expansion and large-scale structure. When light from distant objects is distorted by a foreground galaxy or another massive object, Astronomers can analyze how this lensing alters the appearance of multiple background objects at varying distances. Through this, they can make inferences about the rate at which the universe is expanding and the distribution of matter across it. This information is vital for cosmology, as it helps answer fundamental questions about the universe's composition, growth, and ultimate fate. Moreover, the time delays caused by gravitational lensing open up another fascinating avenue for investigation. When light from a distant quasar or galaxy is lensed by an intervening foreground galaxy, the path that the light takes can differ. This results in noticeable delays in when we observe the light from multiple images of the same background object. By measuring these time delays, astronomers can gain crucial insights into the geometry of the universe, helping them refine measurements of cosmological parameters. As our observations stretch farther into the universe, gravitational lensing continues to shed light on not only the objects being lensed, but also the galaxies that act as lenses, revealing their structures and dynamics. Gravitational lensing in all its forms extends the reach of observational astronomy, offering a window into the history, composition, and fundamental workings of the universe. This expanding tool is helping to unlock the mysteries of space that were once beyond our grasp. As we delve deeper into the universe, artificial intelligence is emerging as a game changer in handling the massive data sets generated by modern astronomical observations. With the rapid advancements in telescopes and space missions, the challenge of processing and interpreting the vast amounts of data has never been more pressing. AI and machine learning are becoming indispensable tools for astronomers, enabling them to unlock insights that would otherwise remain hidden in the data. One of the key applications of AI in astronomy is in the classification of celestial objects. Large surveys, such as the Sloan Digital Sky Survey and the upcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time, catalog millions of stars, galaxies, and other celestial bodies. Traditional methods of data analysis can be time-consuming and labor-intensive, but AI can speed up this process. Machine learning algorithms can be trained to identify patterns in the data, enabling them to rapidly and accurately classify objects. This ability is invaluable for distinguishing between different types of astronomical phenomena, which is essential for subsequent analysis and study. AI also plays a crucial role in extracting meaningful features from complex astronomical data. Sometimes the most important patterns are subtle and not immediately apparent. AI algorithms, especially neural networks, excel in identifying these hidden relationships and trends. They have already been used to identify gravitational waves, detect exoplanets, and even uncover subtle signatures in the cosmic microwave background radiation. With AI, researchers are able to process vast data sets more efficiently, significantly enhancing our understanding of cosmic processes while cutting down on the time required for analysis. Additionally, AI aids in anomaly detection by flagging unusual or unexpected events in astronomical data. The universe is full of rare and transient phenomena, such as supernova, gamma-ray bursts, and other fleeting events that often require immediate follow-up observations. AI can quickly identify these anomalies, allowing astronomers to make timely observations with other instruments. This leads to richer, more detailed data, enhancing our understanding of these rare occurrences and helping scientists piece together a more complete picture of the universe's dynamic processes. In this way, AI is transforming the landscape of modern astronomy, enabling researchers to make sense of an ever-growing flood of data and uncovering new layers of the universe's mysteries. AI has reached a transformative point, becoming an indispensable tool in simulating and modeling celestial phenomena. By leveraging vast data sets, artificial intelligence can create highly sophisticated models that provide insights into complex astronomical processes. These models allow AI to make predictions and generate synthetic data sets, which can then be compared against real-world observations. This capability is invaluable in refining our understanding of the fundamental physics that govern astronomical bodies. Moreover, AI helps refine existing theories about galaxy formation, star evolution, and other cosmic processes. As astronomy advances, integrating AI into research allows us to tackle increasingly intricate challenges, analyze vast quantities of data, and unlock deeper insights into the universe. The potential for AI to revolutionize our approach to studying the cosmos is immense, making it an essential ally for astronomers as they strive to unravel the mysteries of space. One of the most exciting frontiers in space exploration, missions aimed at the farthest reaches of our solar system, often referred to as the edge of the solar system or the outermost boundaries of the heliosphere. These regions, including the Kuiper Belt and the Oort cloud, are still largely unexplored. However, they hold key clues that could shed light on the formation and evolution of our solar system, as well as the environment in which it resides. One crucial area where these missions will make significant contributions is in the study of trans-Neptunian objects, celestial bodies that orbit beyond Neptune. By sending spacecraft to these distant regions, scientists can collect detailed data on the composition, size, and orbital dynamics of these objects. This data is critical for understanding the early conditions that shape the solar system. For example, studying the isotopic ratios of various elements can reveal the processes that influence the formation of the solar system and the role of smaller bodies like planetesimals in the formation of planets. Additionally, missions to the solar system's edge will provide valuable insights into the solar wind and its interaction with the interstellar medium. Understanding how the solar wind interacts with the surrounding galactic environment is essential for refining models of how our solar system fits within the larger structure of the Milky Way galaxy. By measuring cosmic rays and the magnetic field within the heliosphere, scientists can better understand the processes that govern matter's movement and evolution across the galaxy, potentially offering clues to how our galaxy itself evolved over time. Another exciting avenue of exploration is the study of the dynamics of ices and volatiles in the outer solar system. Observations of icy bodies, such as comets and Kuiper Belt objects, provide crucial information about the conditions that existed in the protoplanetary disk during the early days of the solar system's formation. These observations can help scientists understand the processes that transported materials from the outer regions of the solar system to its inner regions, potentially influencing the habitability of Earth and other worlds. Missions to the solar system's edge also promise to refine our computational models of galaxy formation and evolution. By combining data gathered from these missions with other astronomical observations, researchers can refine simulations of how matter interacts and is distributed within galaxies. This holistic approach will enhance our understanding of how galaxies form, evolve, and interact over cosmic timescales. As new missions are planned for the outer solar system, they open up exciting possibilities for investigating the solar system's boundaries in greater detail. The knowledge gained from these missions will not only deepen our understanding of our own cosmic neighborhood, but will also contribute to the broader narrative of galactic evolution, ultimately offering new insights into our place within the Milky Way. Meanwhile, the search for exoplanets has entered an era of unprecedented innovation, with a range of new technologies being developed to detect and characterize distant worlds. These advancements are transforming our ability to discover exoplanets and gather crucial information about their atmospheres, compositions, and potential for habitability. Among the most promising technologies is the use of space-based observatories equipped with advanced photometric capabilities. The James Webb Space Telescope, set to revolutionize exoplanet studies, employs highly sensitive infrared instruments that can detect faint light from exoplanets and analyze their atmospheres. This telescope will utilize the transit method, observing the dimming of a star's light as an exoplanet passes in front of it. This allows scientists to measure the size of exoplanets and gather other vital information about their potential to support life. Moreover, by conducting spectroscopic observations, the James Webb Space Telescope, JWST, will unlock the secrets of exoplanet atmospheres. Through this method, Webb will be able to detect specific atmospheric components such as water vapor, methane, and carbon dioxide. This will provide invaluable insights into the planet's composition and its potential for habitability. Another breakthrough comes from the use of ground-based telescopes equipped with adaptive optics systems. These systems compensate for the distortion caused by Earth's atmosphere, allowing astronomers to directly image exoplanets that are much closer to their host stars. By using advanced techniques, astronomers can minimize the glare from stars, offering a more direct and clearer view of nearby planets and enabling the study of their properties in greater detail. Radial velocity methods have also seen significant improvements. This technique involves measuring the tiny shifts in a star's spectral lines caused by the gravitational pull of orbiting exoplanets. New instruments, such as the espresso spectrograph on the Very Large Telescope in Chile, enhance our ability to detect smaller and less massive planets by improving the precision of these measurements. These advancements are crucial for identifying Earth-like planets located in the habitable zone of their stars. Furthermore, the development of machine learning algorithms plays a pivotal role in handling the vast amounts of data produced by exoplanet surveys. These algorithms can rapidly sift through light curves from telescopes, identifying potential transits of exoplanets with greater efficiency and distinguishing genuine signals from background noise. As datasets continue to grow, machine learning will be instrumental in streamlining the identification process and refining our understanding of exoplanet populations. Collaborative projects, such as the Transiting Exoplanet Survey Satellite, TESS, are revolutionizing the search for new worlds. TESS is designed to scan large portions of the sky, identifying candidates for further study and laying the foundation for subsequent observations with more advanced telescopes. As these new technologies evolve and integrate into the exoplanet research field, they will dramatically expand our ability to discover and study distant planets. The insights gained will deepen our understanding of planetary formation and evolution and bring us closer to identifying potentially habitable planets beyond our solar system. In parallel, neutrino astronomy is emerging as a promising field that could significantly enhance our understanding of galactic phenomena. Neutrinos are subatomic particles with nearly no mass that interact only weakly with matter, allowing them to travel across vast distances in the universe without being absorbed or scattered. This unique property makes neutrinos an exceptional tool for probing cosmic events, especially those occurring in or around our galaxy. One of the key applications of neutrino astronomy is the study of high-energy events, such as supernovae. When a massive star undergoes a supernova explosion, a large portion of its energy is released in the form of neutrinos, which escape the star nearly unimpeded. By detecting these neutrinos, astronomers gain unparalleled insights into the processes happening during the explosion, as well as the dynamics of the progenitor star. Observations of neutrinos from supernovae help refine our models of stellar evolution and improve our understanding of the mechanisms behind these cataclysmic events. Neutrinos also provide critical information about cosmic rays and their origins. Many high-energy cosmic rays are believed to originate from extreme environments, such as supernova remnants, active galactic nuclei, or gamma-ray bursts. When cosmic rays interact with matter, they can produce neutrinos. By studying the neutrino flux associated with these high-energy events, astronomers can gain valuable insights into the acceleration mechanisms and environments responsible for cosmic ray production. Understanding the relationship between cosmic rays and neutrinos enhances our overall knowledge of high-energy astrophysical processes within our galaxy. Neutrino detectors offer an extraordinary window into the heart of some of the universe's most mysterious and energetic phenomena, such as black holes. Neutrinos, those elusive particles born in the extreme environments near black holes, particularly from accretion disks and powerful jets, hold the potential to reveal details about their environments that are otherwise nearly impossible to observe. By identifying and characterizing neutrinos tied to these events, researchers can unlock the hidden processes occurring as matter spirals into black holes or is flung outward at mind-boggling speeds. This ability to probe the invisible allows scientists to piece together a fuller picture of these cosmic titans, shedding light on the mechanics of black hole accretion and jet dynamics. But the study of neutrinos doesn't stop there. It enhances our broader understanding by complementing data gathered from other astronomical messengers, such as electromagnetic radiation and gravitational waves. This multi-messenger approach, where data from multiple sources converge, enables a more robust and comprehensive understanding of complex astrophysical processes. For example, When energetic neutrinos, electromagnetic signals, and gravitational waves are detected simultaneously from an event, they can provide a multifaceted view of the underlying physical phenomena, painting a richer, more detailed picture of the universe's workings. As neutrino detectors continue to evolve with increasing sensitivity and range, the potential of neutrino astronomy is expanding. Future observatories like the IceCube Neutrino Observatory, along with other planned projects in different environments, promise to significantly boost our ability to observe and study these elusive particles. With each new advancement, our understanding of the galaxy will deepen, adding critical pieces to the intricate puzzle of the cosmos. This growing field offers a unique and vital tool for exploring the fundamental forces that govern the universe. At the same time, advancements in radio astronomy are revolutionizing our ability to map the structure of the Milky Way. These breakthroughs are crucial for understanding the formation, dynamics, and overall architecture of our galaxy. Radio waves, unlike other forms of electromagnetic radiation, can penetrate dense dust clouds that often obscure our view of more traditional wavelengths, offering unprecedented access to the inner workings of our cosmic neighborhood. Key to these advancements is the development of large radio telescope arrays, such as the Square Kilometer Array and the Very Large Array. These state-of-the-art facilities employ vast networks of antennas working together to collect data that can be synthesized into high-resolution images of radio emissions from across the Milky Way. With increased collecting areas and enhanced sensitivity, these arrays are able to capture faint signals from distant corners of the galaxy, enabling astronomers to map the distribution of neutral hydrogen, molecular clouds, and other vital elements that make up the Milky Way. Another groundbreaking innovation is radio interferometry, a technique that merges signals from separate radio dishes, effectively simulating the capabilities of a much larger telescope. This advancement has dramatically boosted spatial resolution, allowing astronomers to uncover finer details of cosmic structures. For example, radio interferometry is pivotal in mapping the movements and distribution of gas and stars across various regions of the Milky Way, from its bustling galactic center to its quiet outer reaches. Furthermore, the integration of advanced algorithms and machine learning techniques is transforming the landscape of radio astronomy. These computational tools are increasingly used to process the vast amounts of data generated by radio observations, enabling faster and more efficient classification of celestial objects and phenomena. By automating data analysis, astronomers are able to rapidly extract new insights into the Milky Way's structure, such as the arrangement of stellar populations, star formation regions, and even the influence of dark matter. Together, these advancements are helping to unveil the hidden layers of our galaxy, providing new and invaluable perspectives on the forces that have shaped its formation and continue to drive its evolution. Additionally, the integration of simultaneous multi-frequency observations is paving the way for more comprehensive studies of the Milky Way's structure. By utilizing different radio wavelengths, astronomers can explore various components of the galaxy. For instance, observing hydrogen gas at 21 centimeters allows for the mapping of neutral hydrogen, while tracking different molecular lines like carbon monoxide provides insights into the distribution of molecular clouds, critical for star formation. Moreover, the advancement of pulsar timing techniques, which involve monitoring the regular signals emitted by pulsars, is proving invaluable for studying the Milky Way's overall structure. These measurements help assess the curvature of space and gravity's effects, contributing to our understanding of the galaxy's dynamics and expansion. As these advancements in radio astronomy progress, our ability to map and understand the Milky Way's structure will improve dramatically. The detailed insights gleaned from these observations will deepen our understanding of the galaxy's history, evolution, and the complex processes that shape its vast, intricate architecture. Space-based interferometry offers a groundbreaking method for studying galactic dynamics by providing high-resolution observations of celestial objects and phenomena. This technique combines signals from multiple telescopes or detectors, effectively simulating a much larger aperture to achieve greater sensitivity and resolution than traditional single telescope observations. The primary advantage of space-based interferometry lies in its ability to overcome the limitations imposed by Earth's atmosphere. Ground-based telescopes often suffer from distortions due to atmospheric turbulence, which blurs and degrades image quality. However, space-based interferometers operate outside the atmosphere, enabling astronomers to capture much clearer, sharper images of distant galaxies. This enhanced clarity allows for the observation of fine details in the movements and structures of stars and gas within galaxies, providing invaluable data for modeling their dynamics. By utilizing high-resolution observations from space interferometry, astronomers can significantly improve measurements of stellar motions within galaxies. Understanding how stars move under the influence of gravity helps unravel the complex gravitational interactions that govern galaxy dynamics. For example, detailed observations can reveal the mass distribution within galaxies, shedding light on the role of dark matter and its influence on the orbital dynamics of visible matter. These insights are crucial for refining models of galaxy formation and evolution. Furthermore, space-based interferometry facilitates the study of various galactic features, such as spiral arms, bars, and density waves, by providing precise measurements of their structure and dynamics. Researchers can gather data on how these features evolve over time and their impact on star formation processes. Understanding the interplay between these components is essential for unveiling the mechanisms that shape the overall architecture of galaxies. The capability to observe active galactic nuclei and their associated jets with space-based interferometers also broadens our understanding of galaxy dynamics. Interferometry enables astronomers to resolve the complex interactions occurring near supermassive black holes, studying how they influence their host galaxies and the surrounding cosmic environment. These observations can reveal how energy and matter are transferred and distributed, providing insights into the coevolution of galaxies and their central black holes. Moreover, the ability to conduct precise observations of galaxies at various distances through space-based interferometry enables a comparative approach to studying galaxy dynamics. This approach uncovers how the dynamics of galaxies may differ across cosmic time, revealing evolutionary patterns and the influence of the universe's expansion on galactic behavior. As advancements in space-based interferometry continue, they promise to enhance our understanding of galactic dynamics. By providing detailed, high-resolution data, this technique will deepen our comprehension of the complex forces that govern galaxy formation and evolution, helping us build more accurate models of the universe's structure and development. Quantum computing holds remarkable potential for simulating complex galactic systems, offering capabilities that could significantly advance our understanding of the universe. Traditional computers rely on binary processing, which can become inefficient when tasked with modeling the intricate interactions and vast scales involved in astrophysical phenomena. Quantum computing, on the other hand, leverages the principles of quantum mechanics using qubits to represent and process information in ways that classical computers cannot match. One of the significant advantages of quantum computing lies in its ability to handle complex calculations involving many body interactions, common in astronomical simulations. For instance, simulating the gravitational interactions among thousands or millions of stars within a galaxy can be computationally intensive and time-consuming on classical computers. However, quantum computers can potentially perform these calculations more efficiently, allowing for detailed modeling of stellar dynamics, mergers, and galactic interactions in a fraction of the time currently required. Quantum computing holds immense potential for reshaping our understanding of the cosmos, especially in areas such as molecular dynamics simulations. These simulations are crucial for unlocking the mysteries of star formation and the behavior of interstellar gas and dust. The processes governing the birth of stars from molecular clouds involve complex interactions between particles at the quantum level. Quantum computers, with their ability to model these interactions with unprecedented accuracy, can provide new insights into how stars form, evolve, and shape their surroundings. By harnessing this technology, scientists can gain a deeper understanding of stellar life cycles and their contributions to the chemical evolution of the galaxy. Moreover, quantum computing can revolutionize the analysis of the massive data sets generated by astronomical surveys. The sheer volume and complexity of data from observatories and simulations can overwhelm traditional computational methods, making it challenging to extract meaningful insights. However, quantum algorithms, specifically designed for optimization and machine learning tasks, have the potential to streamline data processing, enabling faster and more comprehensive analysis of galactic phenomena. This could lead to the identification of new patterns, trends, and anomalies, unlocking the door to groundbreaking discoveries about the structures and dynamics of galaxies. Quantum simulations also offer a promising path to unraveling the mysteries of dark matter and dark energy, two enigmatic components that govern the universe's structure and expansion. By accurately modeling the effects of dark matter on galaxies and galaxy clusters, quantum computing can help researchers refine our understanding of its distribution and behavior. This insight is essential for advancing our cosmological models and exploring the fundamental nature of these elusive forces that continue to shape the fabric of the universe. Although quantum computing is still in its infancy, rapid advancements in both hardware and algorithms are opening new frontiers for its application in astrophysics. As scientists continue to develop more powerful quantum systems, the ability to simulate and understand the complexities of galactic systems will only grow, offering profound insights into the formation, evolution, and underlying physical laws of the universe. The integration of quantum computing into astronomical research has the potential to revolutionize our approach to studying the cosmos, providing the tools needed to tackle questions that were once deemed insurmountable. The Milky Way, our home galaxy, is not an isolated entity in the vast expanse of space. Instead, it is an integral part of a much larger cosmic web, a vast interconnected structure that spans the universe. To truly comprehend the Milky Way's place within this grand tapestry, we must examine the cosmos on a variety of scales, from our immediate galactic neighborhood to the farthest reaches of the universe. At the closest scale, the Milky Way belongs to a group of galaxies known as the Local Group, which contains more than 50 galaxies. Among these, the Andromeda Galaxy stands out as the largest and closest major neighbor. The gravitational interactions between the galaxies within the Local Group shape their movements, star formation processes, and overall structure. In particular, the Milky Way and Andromeda, the two dominant galaxies in the group, are on a collision course. In a few billion years, these galaxies will merge, dramatically altering their shapes and their stellar populations. Beyond the Local Group, the Milky Way is part of the Laniakea supercluster, a massive collection of galaxy groups and clusters that spans over 500 million light-years and contains roughly 100,000 galaxies. The gravitational forces of the Milky Way and its neighboring galaxies play a crucial role in the dynamics of this supercluster. Understanding how the Milky Way interacts with other galaxies within Laniakea is essential for deciphering the large-scale gravitational relationships and cosmic flows that define the universe's architecture. On an even grander scale, the universe is structured as a vast cosmic web, made up of filaments of galaxies separated by enormous voids. This intricate structure, sculpted by the distribution of dark matter, dictates the movement of galaxies, including the Milky Way. Galaxies like ours tend to form and cluster along the filaments of this cosmic web, where matter has coalesced, while the voids contain fewer galaxies and sparse matter. The Milky Way's position within this cosmic web profoundly influences its interactions with other galaxies and the distribution of matter in its vicinity. By studying the large-scale structure of the universe, astronomers can begin to unravel the history of galaxy formation and evolution. The patterns observed within the cosmic web offer vital clues about the forces and processes that have shaped the universe over billions of years. As we continue to explore the depths of space, the intricate relationships between galaxies, dark matter, and the cosmic web will provide a deeper understanding of the universe's origin, structure, and ultimate fate. The motion of the Milky Way, when viewed on a cosmic scale, reveals a dynamic and interconnected universe. Our galaxy is not stationary. It is moving toward the Andromeda Galaxy, as well as the Centaurus A galaxy. Additionally, it is being drawn toward the Great Attractor, a massive region of gravitational influence within the Laniakea supercluster. This motion is not just a cosmic curiosity, it offers key insights into the fundamental dynamics that govern the universe. As the Milky Way moves, its interactions within larger cosmic structures shed light on the forces shaping the universe itself. Understanding the galaxy's movement through space helps us grasp the broader patterns of cosmic evolution, where local gravitational influences meet the larger, overarching forces at play. The Milky Way's journey through these immense gravitational regions toward Andromeda, Centaurus A, and the Great Attractor offers a microcosm of the cosmic dance of galaxies throughout the universe. This motion, however, is just one part of the Milky Way's story. Its position and interactions within larger structures contribute to our evolving understanding of the universe's history. The Milky Way's formation, which includes its acquisition of gas and mergers with smaller galaxies, mirrors the processes at work in other galaxies. By studying our galaxy, we are not only learning about its evolution, but also gaining insights into the nature of galactic formation across the universe. In many ways, the Milky Way serves as a critical laboratory for understanding the larger cosmic picture. Scientists examine the dynamics of our galaxy's formation to gain clues about the broader forces that have shaped galaxies throughout the universe over billions of years. In particular, studying the Milky Way's structure and dynamics reveals key information about cosmic phenomena, like the formation of stars and the evolution of galaxies, that have shaped the history of the universe itself. The Milky Way's formation history is one of the most significant areas of study. It began shortly after the Big Bang, through the collapse of gas and dark matter, giving birth to the first stars and structures. By investigating the stars within the Milky Way and their age distributions, researchers can construct a timeline of stellar evolution that matches theoretical models of cosmic development. The discovery of ancient stars in the galactic halo and bulge provides important clues about the early universe and the conditions during the first generations of star formation. Moreover, the Milky Way offers a glimpse into how interactions and mergers between galaxies influence their evolution. Throughout its history, the Milky Way has collided with and absorbed smaller dwarf galaxies, growing in mass and enriching its chemical composition. These mergers and their aftermath provide a roadmap for understanding how galaxies grow, accumulate mass, and evolve over time. The dynamics we observe in our galaxy reflect similar processes in other galaxies, allowing scientists to draw parallels and better understand the statistical processes driving galaxy formation across the universe. The Milky Way's spiral structure is another crucial aspect of galactic evolution. It serves as a model for understanding the dynamics of barred and spiral galaxies throughout the cosmos. Observations of gas dynamics, star formation rates, and the influence of dark matter reveal how gravitational forces shape these structures. By studying the Milky Way's mechanisms for regulating star formation and distributing matter, astronomers can make broader inferences about the fundamental processes at work in other spiral galaxies. Another critical area of study is the Milky Way's chemical composition. Elements heavier than hydrogen and helium, created inside stars, are scattered into the interstellar medium through supernovae and stellar winds. By analyzing the metallicity of stars across different regions of the Milky Way, astronomers can trace the history of element formation in our galaxy. This, in turn, provides valuable insights into the chemical enrichment process that has shaped the matter distribution in galaxies, offering clues to how elements have spread across the universe over time. In essence, the Milky Way is a living laboratory, offering a detailed look at the processes that shape galaxies. Studying our galaxy's motion, structure, and composition not only deepens our understanding of the Milky Way itself, but also illuminates the broader patterns of cosmic evolution. Through this, we can appreciate the complexity of the universe and the intricate dance of forces that continue to mold the cosmos. The Milky Way's interaction with its surrounding environment, especially its position within the local group and the Laniakea supercluster, opens a window into the broader architecture of the universe. By studying how galaxies behave within clusters and superclusters, we can refine our understanding of cosmic evolution. This includes grasping the distribution of dark matter, the effects of cosmic expansion, and the varied behaviors of different galaxy types. As new observations and technological advancements provide increasingly detailed data on the Milky Way, our insight into its pivotal role in the universe's evolution will continue to deepen. The knowledge we gain from our galaxy acts as a guide to understanding the vast array of galaxies observed across the cosmos, helping to enhance our comprehension of the complex relationships and processes that govern cosmic development over time. The chemical composition of the Milky Way galaxy serves as a living archive of cosmic history. It reflects the processes and events that have shaped the universe since the Big Bang, offering clues to stellar evolution, nuclear synthesis, and the dynamic cycles of matter that play out across the galaxy and beyond. In the earliest stages, the universe consisted mainly of hydrogen and helium, the simplest elements formed during Big Bang nucleosynthesis. Over time, stars began to form from this primordial gas. Through their life cycles, these stars fused lighter elements into heavier ones, a process known as nuclear fusion. The most massive stars, after burning through their nuclear fuel, exploded in violent supernovae, ejecting these heavier elements back into the interstellar medium. This continual enrichment of the galactic gas over millions to billions of years creates a cycle where new stars are born from material altered by previous generations. By studying the chemical composition of stars throughout the Milky Way, astronomers can unlock the history of this ongoing enrichment process. For instance, ancient stars in the galactic halo and bulge tend to have lower metallicities, a sign they formed early in the galaxy's life when there were fewer heavy elements available. By examining these ancient stars, researchers can deduce the conditions in the early universe and the timescales over which stars generated and spread heavier elements. In contrast, stars formed in regions with higher metallicity typically resulted from gas that had already been enriched by prior stellar generations. The distribution of metallicity from the core of the Milky Way to its outer regions reveals the dynamic processes of gas inflow and outflow, star formation rates, and the influence of galactic motion. The variation in metallicity offers crucial clues about how interstellar gas is recycled throughout the galaxy, contributing to the formation of planets and other celestial bodies. Moreover, studying specific elements and their ratios provides further insight into the diverse stellar processes at play. For instance, elements like carbon and oxygen are predominantly produced inside medium-mass stars and released during their later stages as red giants. On the other hand, supernovae are responsible for producing elements such as iron and nickel. By analyzing the abundance of these elements in different stellar populations, astronomers can trace the history of star formation and the types of supernovae that have shaped the galaxy. The Milky Way, a sprawling cosmic entity, holds the key to unlocking some of the universe's deepest secrets. Its chemical composition is intricately tied to the forces shaping the galaxy, such as its interactions with neighboring galaxies and the elusive intergalactic medium. Processes like mergers and accretion act as cosmic gateways, funneling new gases and elements into the Milky Way. These forces do more than just add matter. They play a pivotal role in determining the galaxy's chemical evolution. When we trace the movement of gas and observe how it flows through the galaxy, we begin to see a clear picture emerge. This flow shapes the galaxy's enrichment, offering us profound insights into the interconnectedness of galaxies across the universe. By studying these intricate chemical processes, we are able to peer into the Milky Way's past. This chemical signature reveals a record of events that stretch back to the very inception of the universe, a history written in the stars. Through these revelations, scientists gain valuable insights into stellar evolution, nucleosynthesis, and the dynamic cycles that govern the cosmos. The Milky Way acts as a living laboratory, showcasing the ongoing story of how matter, energy, and life are woven together across cosmic time. By studying its rich chemical makeup, we can decipher the universe's underlying rhythms and patterns. The Milky Way also serves as an indispensable tool for testing cosmological theories. Thanks to its proximity and detailed study, the galaxy provides astronomers with a unique opportunity to examine and refine models of galaxy formation, evolution, and the fundamental forces shaping the universe. With its well-charted structure, The Milky Way is the benchmark against which cosmological models can be validated. As scientists measure its properties, they're able to assess how accurately these models predict galactic behaviors and the interactions that define cosmic growth. A particularly crucial area where the Milky Way plays an instrumental role is in the study of dark matter. Cosmological models predict that the dark matter constitutes a significant portion of the universe's mass, profoundly influencing both large-scale structures and the behavior of individual galaxies. By observing the rotation curve of the Milky Way, how the speed of stars varies with their distance from the galactic center, astronomers can infer the presence and distribution of dark matter. These observations challenge, confirm, and refine our understanding of dark matter's role in shaping galaxies, their dynamics, and their formation. In the broader context of the universe, the Milky Way is a living fossil, preserving the history of galaxy formation and evolution. Theories suggest that galaxies grow over time through mergers and interactions with smaller galaxies, a process that has contributed significantly to the Milky Way's growth. By studying the Milky Way's interactions with nearby satellite galaxies, such as the Large and Small Magellanic Clouds, researchers can test models of hierarchical structure formation. These patterns offer crucial evidence about how galaxies merge, interact, and evolve, affecting everything from their morphology to their star formation rates. Moreover, the Milky Way's chemical makeup holds the key to understanding nucleosynthesis, the process by which elements are formed in stars and supernova, and the chemical enrichment that has taken place over cosmic history. By examining the abundance of different elements in various stellar populations, astronomers can assess the validity of models describing the evolution of matter in the universe. These chemical traces provide a timeline for how galaxies have formed, matured, and evolved over vast stretches of cosmic time. Finally, the Milky Way stands as a crucial anchor for cosmological measurements that help map the broader universe. Take the Hubble constant, for example, which describes the rate at which the universe is expanding. By measuring distances to objects within the Milky Way, using methods like parallax, researchers can set benchmarks that inform larger-scale measurements. This allows for the Hubble constant, derived from local observations, to be compared with values obtained from distant galaxies, offering a powerful way to test the consistency of cosmological models and refine our understanding of the universe's expansion. In every corner of the Milky Way, from its swirling arms to its hidden depths, lies a story that not only reveals the galaxy's past, but also shapes our understanding of the cosmos itself. The study of our galaxy within the framework of the cosmic web offers invaluable insights into the grander scale of galaxy interaction and evolution. By observing the Milky Way and its neighboring galaxy groups, scientists can unravel how our galaxy fits into the vast, intricate structures of filaments and voids, as predicted by cosmological models. This broader understanding paints a clearer picture of how galaxies like ours interact over cosmic time, influencing their development in ways we're only beginning to grasp. In conclusion, the Milky Way acts as an essential reference point for testing and refining various aspects of cosmological theories. Its detailed study allows researchers to probe deeply into the mysteries of dark matter, galaxy formation, chemical evolution, and the expansion of the universe. What we learn from studying our own galaxy contributes directly to our understanding of the cosmos as a whole. Through our galaxy, we glimpse the complex dynamics that govern the universe, providing a foundation upon which our broader theories are built. The Milky Way serves as a critical model for understanding the distribution of matter throughout the universe. By examining the components of our galaxy, its stars, gas, dust, and dark matter, we gain a more complete picture of the structural dynamics at play in the cosmos. One of the most revealing aspects of this is the study of our galaxy's rotation curves. Observations show that the velocities of stars and gas don't decrease as expected with distance from the galactic center. Instead, they remain unexpectedly constant, a clear indication that there's a massive amount of unseen mass, what we call dark matter, influencing these movements. This discovery allows scientists to map the presence of dark matter across the galaxy and understand how it's distributed both here and in other galaxies. Gravitational lensing, another key phenomenon tied to the Milky Way, offers another important clue about mass distribution. When light from distant objects passes through the gravitational field of a massive object such as our galaxy, it bends. This bending of light allows astronomers to trace how dark matter is distributed by observing the distortions in the light. By studying the way light is lensed across different regions of the Milky Way, scientists can infer not just the distribution of visible matter, but also the invisible dark matter shaping the structure of our galaxy and the cosmos at large. Beyond the galactic scale, the Milky Way also reveals secrets about the intergalactic medium, the diffuse gas that exists between galaxies. Observations of how our galaxy interacts with its surrounding gas clouds, as well as its nearby satellites, provide insights into the flow of material between galaxies and the intergalactic space. These interactions not only affect star formation within the Milky Way, but also influence the exchange of matter across galaxies, shaping the overall distribution of matter across the universe. This exchange plays a vital role in the broader cosmic cycles of matter. The chemical composition of the Milky Way's stellar populations also offers a timeline of the evolution of matter. By analyzing the formation rates of stars and the abundance of specific elements, scientists are able to trace the enrichment of the universe over time. This process reveals how the first generations of stars seeded the cosmos with heavier elements, which were later incorporated into the next generation of stars, planets, and even life itself. The Milky Way, then, not only provides insight into the present-day distribution of matter, but also allows us to peer back in time, learning how matter has been recycled and redistributed over billions of years. Through all these observations, the Milky Way remains central to our exploration of the cosmos. Each discovery brings us one step closer to understanding the intricate dance of visible and dark matter that shapes the universe. Its story is, in many ways, the story of the universe itself, constantly evolving, constantly revealing its secrets. In addition, the positioning of our galaxy within the cosmic web, an intricate network of filaments and voids shaped by dark matter, offers a glimpse into the larger scale organization of matter throughout the universe. By examining the interactions between the Milky Way and its neighboring galaxies in the local group, as well as its place in the vast Lanaka supercluster, researchers are able to study the role of gravitational forces in shaping the distribution of galaxies. This helps us understand how cosmic structures form and evolve over time. Studying the Milky Way provides vital insights into the universe's matter distribution, as it reveals the dynamic relationship between visible and dark matter. It also offers a window into the interactions with the intergalactic medium and traces the historical processes that have shaped matter's evolution. The knowledge we gain from examining our galaxy deepens our understanding of the broader cosmic environment, allowing researchers to create more accurate models of how matter is organized and distributed across the universe. The Milky Way's satellite galaxies play a crucial role in this process. As these smaller galaxies orbit the Milky Way, they act as natural laboratories where scientists can study the dynamics and interactions that shape galactic structures. The properties and behaviors of these satellite galaxies, along with the patterns of their distributions, offer valuable insights into how galaxies form and evolve over cosmic time. One of the most significant aspects of these satellite galaxies is how they highlight the influence of gravity and dark matter on galactic formation. Many of these satellites are made predominantly of dark matter, and studying their interactions with the Milky Way can reveal how dark matter affects galaxy dynamics. For example, observing the orbits and velocities of these satellites allows researchers to measure the gravitational potential of the Milky Way's dark matter halo. Understanding how these dwarfs respond to gravitational forces can help refine models of dark matter distribution not only in the Milky Way, but also in other galaxies. Additionally, the composition of the Milky Way's satellite galaxies provides key insights into their formation and evolution. Many of these satellites are old and metal poor, indicating that they formed early in the history of the universe. By studying their stellar populations and chemical compositions, researchers can unravel the processes that led to the formation of smaller galaxies and learn more about the role of environmental interactions in their evolution. For instance, examining the distribution of different stellar populations within these satellite galaxies can help inform theories about star formation rates and the influence of feedback mechanisms such as supernovae or cosmic rays. Furthermore, the interactions between the Milky Way and its satellite galaxies offer valuable information about tidal forces and their implications for structure formation. The gravitational pull of the Milky Way causes tidal stripping, a process where smaller satellite galaxies lose their gas and stars, gradually dissolving into the Milky Way's halo. Studying these processes helps scientists understand how larger galaxies grow through the accretion of smaller ones, and how satellite galaxies contribute to the overall mass and structure of their larger neighbors. Through these observations, we not only gain a deeper understanding of our own galaxy, but also piece together a broader picture of how galaxies form, evolve, and interact across the universe. The distribution and variety of satellite galaxies around the Milky Way offer crucial insights into the statistical properties of galaxy formation. In the hierarchical structure formation model, the number, sizes, and types of satellites help researchers piece together the history of galaxy mergers and the evolutionary process of the Milky Way itself. By comparing the Milky Way's satellite system with that of other galaxies, like Andromeda, astronomers are able to probe the commonalities of these processes. This comparison refines theories about galaxy formation in different environments, providing a broader context for understanding cosmic evolution. The Milky Way's satellite galaxies serve as a key to unlocking the mysteries of structure formation across the universe. These dwarf galaxies offer invaluable data on the effects of dark matter, star formation, tidal interactions, and galaxy mergers. Studying them helps astronomers develop a more complete picture of galaxy evolution, which in turn informs models of cosmic structure formation. Through this, our understanding of the universe's history and dynamics deepens. The Milky Way's dark matter halo plays an essential role in the structure of our galaxy, influencing not only its gravitational pull, but also our broader understanding of galactic dynamics. Dark matter halos are vast, invisible regions surrounding galaxies that exert gravitational force. These halos vary in size, shape, and density across different galaxies. By comparing the Milky Way's dark matter halo with those of other galaxies, scientists gain a deeper understanding of the formation and evolution of galactic structures. One striking feature of the Milky Way's dark matter halo is its mass and distribution. Studies indicate that the halo's mass is approximately 1 trillion solar masses. While this is significant, it's not unusual for spiral galaxies. The density profile of the Milky Way's dark matter halo follows a pattern that aligns with the predictions of the standard cold dark matter model. This model suggests that dark matter density decreases with distance from the galaxy's center, meaning the inner regions are more concentrated, while the outer regions have a more diffuse distribution. When comparing the Milky Way's dark matter halo to those of galaxies like Andromeda, astronomers observe both similarities and differences. Andromeda also boasts a substantial dark matter halo, similar in mass to the Milky Way's. In the distant future, the two galaxies are expected to merge. This eventual collision offers astrophysicists a rare opportunity to study how dark matter dynamics change in response to gravitational interactions during merger events, deepening our understanding of galactic evolution in such extreme environments. Dwarf galaxies provide a fascinating contrast to their larger counterparts, like the Milky Way, especially when it comes to the characteristics of their dark matter halos. These halos, which surround galaxies and influence their dynamics, reveal much about the formation and evolution of galaxies across the universe. Unlike the halos of larger galaxies, which tend to have a more uniform, spherical shape, those in dwarf galaxies often exhibit significant differences. Dwarf galaxies typically have lower surface brightness and irregular dark matter density profiles. Some of these halos are less massive, while others are shaped by the specific history of the galaxy's formation. Their structure can range from nearly spherical to highly irregular, reflecting a diverse range of formation processes. By observing the halos of various dwarf galaxies, scientists are able to probe how environmental factors and galactic interactions influence dark matter. These observations are crucial in understanding the role of dark matter in shaping not just individual galaxies, but also the broader gravitational field that holds galaxies and their clusters together. Even more distant galaxies, far beyond the reach of the Milky Way, reveal critical information about dark matter distribution. Gravitational lensing, a technique that uses the bending of light by massive objects, allows astronomers to map the dark matter halos of galaxies at various distances. These observations have revealed halos that deviate from the expected spherical shape, showing elongated or irregular structures. This unexpected diversity provides crucial insights into how different formation histories and environmental factors influence dark matter distribution. Comparing the dark matter halo of the Milky Way with those of other galaxies further refines our cosmological models. These comparisons offer an invaluable context for interpreting galaxy behaviors and enhance our understanding of the universe's large-scale structure. This, in turn, shapes our understanding of how dark matter influences galaxy formation and evolution. The interplay between galaxies, dark matter, and cosmic evolution becomes clearer as these intricate relationships are unraveled. The Milky Way itself serves as a treasure trove of knowledge on galaxy evolution, offering a nearby and relatively well-understood example of a spiral galaxy. By studying its structure, dynamics, and history, astronomers gather essential insights into the processes that govern galaxy formation across the cosmos. A key area of interest is star formation, which plays a central role in shaping the development of galaxies. The Milky Way, with its varied rates of star formation across different regions, the galactic disk, bulge, and halo, provides a unique opportunity to investigate the factors that drive or inhibit star formation. By analyzing the distribution of young and old stars, as well as the gas and dust that fuel this stellar birth, scientists can uncover the conditions that shape a galaxy's evolution. The Milky Way's complex relationship with its satellite galaxies offers further insights into galaxy dynamics. Over time, the Milky Way has absorbed smaller galaxies through gravitational interactions, a process known as accretion. These interactions are pivotal in understanding how galaxies grow, both in mass and in structural complexity. The remnants of these accretion events provide valuable clues about the Milky Way's past mergers, its stellar population, and its dark matter content. By studying the chemical composition of stars in the Milky Way, researchers can trace the history of nucleosynthesis, the process by which stars produce elements, and the recycling of materials throughout the galaxy. Each generation of stars contributes to the chemical enrichment of the interstellar medium. When stars explode as supernovae or shed their outer layers, they release heavy elements into space, enriching the galaxy's gas and dust. By studying the abundance of these elements across different stellar populations, astronomers can reconstruct the timeline of element formation and their distribution across the Milky Way. This knowledge is vital for understanding how elements produced in stars eventually lead to the formation of planets and possibly the conditions necessary for life. The Milky Way also provides a clear example of the role of dark matter in galaxy evolution. Surrounding the galaxy is a massive dark matter halo, which influences the motion of both stars and gas within it. By studying the gravitational effects of this dark matter, astronomers can infer its properties and distribution. These studies contribute to refining our models of how dark matter interacts with ordinary or baryonic matter. Understanding these interactions offers key insights into how galaxies have formed and evolved under the influence of dark matter over cosmic time, revealing the hidden forces that govern the structure and behavior of our universe. The Milky Way's position in the vast expanse of the universe holds a crucial key to understanding galactic evolution. Its placement within the local group and the larger Laniakea supercluster is not just a backdrop, it's central to the forces shaping its development. These galactic clusters provide a unique environment, influencing how galaxies evolve in response to their surroundings. The intricate relationships between the Milky Way and its neighboring galaxies reveal how gravitational interactions, mergers, and the broader cosmic web contribute to their formation and evolution. Studying the Milky Way offers more than just a glimpse into our own galaxy. It's a window into the very processes that govern galaxy evolution across the cosmos. from the birth of stars to interactions with satellite galaxies. From chemical enrichment histories to the role of dark matter, the Milky Way's story is a microcosm of the larger universe's history. As astronomers continue to gather data and refine their models, these discoveries will enhance our understanding of how galaxies, like the Milky Way, have shaped and continue to shape the universe. The star formation history of the Milky Way is intricately linked to broader cosmic star formation rates, providing vital insights into how galaxies evolve over time. By examining how our galaxy's star formation compares to universal trends, astronomers can assemble a larger narrative of galactic evolution and the processes that drive star formation on a cosmic scale. Throughout its history, the Milky Way has seen fluctuating rates of star formation, shaped by factors like gas availability, environmental conditions, and interactions with neighboring galaxies. Studies of its stellar populations suggest that major bursts of star formation occurred at different points in its timeline. For instance, between 5 to 11 billion years ago, the Milky Way experienced a vigorous phase of star formation, a period when the rate of new stars being born far outstripped today's levels. This historical lens allows scientists to correlate the Milky Way's star formation rate with the larger cosmic star formation rate over time. Cosmic surveys reveal that star formation in the universe peaked around 10 to 12 billion years ago, during an era known as cosmic noon. This period marked a time when galaxies, including those similar to the Milky Way, underwent a major burst of star creation. By comparing our galaxy's star formation history to these broader cosmic trends, astronomers gain valuable insights into how star formation processes in the Milky Way mirror those in other galaxies. Furthermore, models describing the decline in star formation rates over the last several billion years align with observations in the Milky Way. Our galaxy, too, has witnessed a gradual reduction in star formation activity following the cosmic trend. This decline is not just a sign of aging, it's also a reflection of how galaxies, including our own, respond to their environments over time. The relationship between local and cosmic star formation rates also highlights the significant influence of environmental factors and galactic interactions. When smaller galaxies merge with the Milky Way, they can trigger bursts of star formation, spurred by the influx of gas and gravitational forces at play. These hierarchical processes tie the Milky Way's star formation history to the larger mechanisms that shape star formation rates across the universe. In the grand tapestry of the cosmos, the story of the Milky Way's evolution is more than just the history of one galaxy. It's a chapter in the universal saga of star formation, galactic interaction, and the ever-evolving dance of the universe itself. The Milky Way galaxy, our cosmic home, offers an unparalleled opportunity to explore the fundamental forces that shape the universe. By studying its complex processes, we gain invaluable insights into star formation, evolution, and the broader mechanisms that govern galaxies across the cosmos. One of the galaxy's most fascinating features is its star formation feedback mechanisms, phenomena like supernova explosions and stellar winds. These processes do more than just illuminate the night sky. They actively regulate the rate of star formation within galaxies. By either expelling gas from star-forming regions or enriching the surrounding space with heavy elements, they shape the very future of cosmic evolution. Understanding these feedback processes is essential, not just for our understanding of the Milky Way's past, but for interpreting the broader trends observed in galaxies across the universe. The star formation history of our galaxy provides a crucial context for assessing universal star formation rates. It allows scientists to draw connections between the local, intricate processes happening in our own galaxy and the broader patterns seen in distant galaxies, offering a clearer picture of the universe's evolution. In studying the Milky Way's history, astronomers are uncovering patterns that reveal how stars are born and evolve. These revelations help us understand the cosmic mechanisms that drive the formation and growth of stars, a process central to the very existence of galaxies, planets, and life itself. The Milky Way, standing out among billions of galaxies, provides us with a unique lens through which to study these forces, thanks to its particular blend of characteristics. As an L-spiral galaxy, the Milky Way boasts a structural form that includes a central bar-shaped region of stars, spiral arms that extend outward, and a surrounding halo of stars and dark matter. This specific arrangement influences the galaxy's dynamics, including the way stars are born and evolve. The combination of the bar and spiral arms offers astronomers a unique opportunity to study how such structures form and change over time, serving as a representative example of similar galaxies scattered throughout the universe. Moreover, the Milky Way's proximity to our solar system offers another remarkable advantage. It serves as a local and well-studied environment, acting as a cosmic laboratory where astronomers can observe galactic processes with unprecedented detail. The vast array of data collected from across the electromagnetic spectrum, from radio waves to X-rays, provides us with a comprehensive view of the galaxy's many components, including stars, gas, dust, and dark matter. This proximity allows for high-resolution observations that would be nearly impossible to achieve from distant galaxies, enabling a deeper understanding of our cosmic neighborhood. The Milky Way's diverse composition further enriches our study of the cosmos. It is home to a wide variety of stellar populations, from ancient stars in the halo to younger, actively forming stars within its spiral arms. Its chemical makeup, shaped by billions of years of stellar nucleosynthesis, holds vital clues about the processes that govern the creation of matter in the universe. These stars and their accompanying elements not only shape our understanding of galactic evolution, but they also provide a roadmap for the conditions that could lead to life-friendly environments. In the neighborhoods of star formation, where heavy elements are distributed, we can trace the origins of planets and the potential for life beyond our own world. By continuing to explore the Milky Way, astronomers are not just piecing together the history of our galaxy. They are uncovering universal truths that stretch across the cosmos. Through this journey, we come closer to understanding how stars, galaxies, and the conditions necessary for life came to be, revealing the intricate dance of forces that shape the universe itself. Moreover, the Milky Way's interactions with its satellite galaxies, including the Large and Small Magellanic Clouds, stand as a remarkable example of galactic evolution through mergers and accretion. The continuous gravitational interactions, combined with the powerful effects of tidal forces, reveal critical insights into the mechanisms driving galaxy growth. These interactions not only illuminate the processes shaping stellar populations and dynamics over time, but also offer clues into the evolution of galaxies themselves. Another striking feature of the Milky Way is the presence of the supermassive black hole at its core, Sagittarius A Sti. Studying this immense black hole and its gravitational influence on the surrounding stellar environment unveils the intricate relationship between central black holes and the properties of their host galaxies. Research surrounding Sagittarius A Sti provides a deeper understanding of the role black holes play in shaping galaxy formation and evolution, shedding light on their fundamental role in cosmic development. Finally, the Milky Way plays a unique and pivotal role in the search for extraterrestrial life. Its vast array of star systems, many of which host potentially habitable planets, discovered through extensive exoplanet studies, suggests that life beyond Earth may be possible. Investigating the conditions within our galaxy that foster the emergence of life is an exciting frontier in the field of astrobiology, offering a glimpse into what might lie beyond our own planet. The Milky Way's distinctive characteristics, its barred spiral structure, its proximity allowing for detailed study, its diverse stellar populations, the interactions with its satellite galaxies, the central supermassive black hole, and its potential for hosting extraterrestrial life, set it apart from the countless galaxies in the observable universe. These features provide essential insights into the processes that drive the formation and evolution of galaxies, and enhance our broader understanding of cosmology and the intricate unfolding of the universe itself.